4 light-years away, the closest star system to Earth is supposed to be familiar, predictable, almost solved. But when James Webb stared into Alpha Centauri in infrared, it found a glow that shouldn't be there. A pattern that doesn't match the story we've been telling ourselves. Is it hidden planets, strange dust and chemistry, or the first hint that our nearest neighbour might be alive? In the nearest stellar neighbourhood, every photon should behave, yet Webb's infrared ledger shows entries no one can balance. Across Alpha Centauri, heat and shadow trade places, and the margins refuse to stay clean. Because Alpha Centauri is so close, we expect it to be straightforward, an exoplanet lab we can finally read without guessing. Yet closeness is not clarity. When overwhelming brightness floods detectors and stacks signals into one crowded scene. There are 3 suns here, and they do not sit politely in a diagram. Alpha Centauri A and B circle each other in a long elliptical dance, their gravity sculpting space as they trade distance and warmth. Farther out, Proxima drifts like a loosely tethered spark, small, dim, and capable of sudden violence. If something looks unusual in infrared, the first task is not belief, but separation. What belongs to the stars? What belongs to the space between them? In Webb's bands, temperature becomes a language, and the system speaks in gradients and slopes. Dust can glow like a planet can hide inside glare, and a binary can carve rings that imitate intent. Even the telescope has fingerprints, diffraction, persistence, scattered light that can masquerade as structure unless challenged from every angle. So our question becomes sharper and more demanding. What physical source can produce the pattern Webb records, repeatedly under scrutiny? Is it a warm exozodiacal cloud sustained long after it should have faded? Or a collision still echoing through old orbits? Is it a world whose heat leaks through the darkness, moving with clockwork over months as gravity dictates? Or is it a lesson in humility, where the anomaly dissolves as we learn to subtract the instrument from the sky? The stakes reach beyond a single curiosity, because dust is not just scenery, it is fog in front of planets. It can drown out biosignatures, or betray the collisions that deliver water and organics to habitable zones. And in Proxima's tight, flare-battered ring of temperate light, atmospheres may be built, stripped, and rebuilt again. To interpret any hint of habitability here, we must first master the system's shifting background, its dynamics, its chemistry, its noise. Alpha Centauri tempts us with proximity, but it tests us with complexity, demanding evidence that survives time, wavelength, and method. Over the next hour, we will watch that evidence take shape, one constraint at a time, until the strange becomes legible. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will track the system's moving geometry, then follow Webb's data through the gauntlet of models, artifacts, and competing explanations. And when the clues finally cohere, they will redefine how we search for worlds and for life around the stars closest to home. .37 light-years away, Alpha Centauri feels like a solved problem, almost like a star chart annotation we have already outgrown. It is the nearest star system, the closest plausible destination for future probes, and our best testbed for exoplanet science next door. In cosmic terms, it is practically across the street, close enough that its motion against background stars can be tracked with remarkable accuracy. Yet proximity does not guarantee clarity, and in astronomy it often does the opposite. The closer a system is, the more its details crowd the data, piling signal on top of signal. Bright starlight saturates detectors, dust glows where planets should hide, and gravity keeps rearranging the scene. Even the simple act of separating star from environment becomes a careful accounting problem. Alpha Centauri is not one star, and it never behaves like a single point of light. It is a moving three-body neighbourhood with overlapping light, heat, and debris, and our instruments must disentangle those layers in real time. If we want to know what is strange in Webb's view, we first need the system's geometry, its choreography, its scale, and its shifting angles. Alpha Centauri A and Alpha Centauri B form a tight binary, and they dominate the system's gravitational architecture. They orbit a shared centre of mass on a long elliptical path that changes their separation over decades. At their closest, they draw near enough to complicate any surrounding disk, and at their widest, they open temporary space for stable structures to persist. Their combined gravity can sculpt dust into rings, gaps, and clumps that look like planetary signatures, even when no planet is present. In a binary system, resonances can trap grains in preferred locations, and repeated gravitational nudges can clear other regions. What looks like a clean gap might be a planet, or it might be the binary's rhythm carving the dust like a slow metronome. Visually, the pair can be imagined as two bright lanterns sweeping around one another, their overlapping halos washing the same patch of space from different angles. As they move, the pattern of illumination changes, and dust grains respond by warming and cooling. That shifting thermal map matters because Webb does not just see light, it sees heat. Farther out, Proxima Centauri drifts as a loose companion, and its presence makes the system feel both connected and fragmented. It is bound to the pair, but at a vastly larger distance, so large that the inner binary can seem like a separate system. Proxima's orbit is slow and uncertain on human timescales, because its period is likely hundreds of thousands of years. Its position complicates how we define the system's true boundary, and it reminds us that Alpha Centauri is not a single target but a nested hierarchy. This is the nearest laboratory for planetary formation under multiple suns, and that phrase is not just poetic. Binary stars change the physics of disks by adding time-dependent gravity and variable heating, which can alter how planetesimals collide and stick. It is also the nearest place where habitability arguments can be tested with real measurements, not just statistics, because the stars are bright enough for precise characterization. If Earth-like planets exist anywhere close, they are most likely here, at least in the sense that we can search with the highest sensitivity. Alpha Centauri A is sun-like in mass and temperature, and Alpha Centauri B is slightly cooler and smaller, which shifts where a temperate orbit might lie. With two different stellar environments in one system, we can compare how similar starting conditions lead to different outcomes. That is why the stakes are immediate, and why every ambiguous data point feels consequential. A confirmed planet around A or B would reshape mission designs, target lists, and timelines for interstellar exploration. Even a dust environment more intense than ours would change what instruments must overcome, because dust is not just scenery, it is noise, and sometimes it is a wall. Historically, Alpha Centauri has always tempted astronomers with the promise of certainty, and it has repeatedly refused to cooperate. Its closeness made it a classic target for early astrometry and radial velocity work, yet the very brightness that helps also creates systematic challenges. Each generation of instruments brings a new claim, a new correction, and a new reminder that nearby does not mean simple. The mystery begins with infrared. In Webb's observations, there are hints of an excess and an asymmetry that do not sit neatly on a simple stellar model. The signal is tentative, and it is not presented as a discovery, which is exactly what makes it compelling. It is a clue that demands an investigation, because it sits in the narrow space between instrumental quirk and new astrophysics. An infrared excess can mean several things, and each possibility carries a different story about the system. It can be warm dust close to a star like an amplified zodiacal cloud, where countless tiny grains scatter and radiate. It can be a circumstellar belt, a circumbinary structure, or transient material stirred by the binary's changing gravity. It can also be a planet's thermal glow or the indirect imprint of planets shaping dust into patterns. To picture this, imagine a faint smoky veil near the stars, glowing not by reflected sunlight but by its own warmth. Dust grains absorb starlight and re-emit it at longer wavelengths, and that re-emission peaks in the infrared depending on temperature. A small shift in temperature can move emission from one band to another, so the spectrum becomes a thermometer as well as a fingerprint. But it can also be none of those, and that is not a cynical caveat, it is a core part of the method. Bright nearby stars are where systematic errors thrive because the detectors are pushed toward their limits. Detector nonlinearity, scattered light, imperfect subtraction, and calibration limits can create features that mimic real astrophysical structure. When a star is this bright, the instrument's own optics become part of the scene. So the question is framed carefully, with a discipline that modern exoplanet science has learned the hard way. What exactly is strange in Webb's infrared view of Alpha Centauri, and how stable is that strangeness across different processing choices? Is it an unseen planet? unexpected dust in chemistry, a transient structure, or an artifact of how we observe brilliant stars? The difference between those answers is the difference between a headline and a footnote. To understand why Webb is central, we need to understand why infrared matters and why it changes the rules of visibility. Optical telescopes mostly see reflected starlight, and that is a brutal regime for close-in planets. Planets and dust near a star are drowned in glare at visible wavelengths, because the star outshines them by factors of millions to billions. In the infrared, the rules shift, because temperature becomes a source of light. Warm dust emits its own thermal radiation, and its brightness depends on grain size, composition, and distance from the star. Young or massive planets can glow, and even older planets can stand out at the right wavelengths if the contrast is favourable. Infrared does not remove the star, but it changes the contrast game, and it gives us new levers to pull. JWST was built for this regime, and its design reflects decades of lessons from earlier infrared missions. Its near-infrared and mid-infrared sensitivity can detect faint heat signatures that older observatories missed, especially when the background is carefully controlled. It can map subtle spectral slopes and brightness distributions that hint at temperature, composition, and particle size. In plain terms, it can tell us whether we are seeing hot dust, cooler dust, or something that behaves like a compact object. Still, Webb is not a magic planet camera, and the documentary's tension depends on that limitation. It cannot simply photograph an Earth twin next to a Sun-like star at 4 light-years, because the angular separations are small and the contrast is extreme. The stars are bright, the diffraction pattern is complex, and the system's dust can be brighter than the planets we seek. Even with advanced processing, the star's residual light can masquerade as structure. That limitation is part of the suspense, because it forces interpretation rather than simple recognition. The same infrared glow that could be a planet can also be a dust belt, and those two possibilities can overlap in brightness. The same asymmetry that could be a gravitational wake can also be a background source or a subtraction residual. Every candidate explanation must survive a gauntlet of alternative causes. Alpha Centauri makes that ambiguity worse because it is dynamic, and dynamics create changing baselines. A and B move relative to each other, changing illumination patterns and gravitational resonances, and those changes can modulate dust emission. Dust can be trapped, shepherded, or destabilized as the binary orbit evolves, and the resulting structures can be temporary. A feature seen at one epoch might fade, shift, or reconfigure as the system continues its slow dance. If there are planets, they must survive in a shifting gravitational landscape, and stability is not a guess here. Stable orbits exist, but they are constrained by the binary's separation and eccentricity, and by the planet's distance from its host star. Planets close to A or B must remain inside stable zones, while circumbinary planets must orbit far enough out to avoid disruption. These are not just theoretical curves, they determine where we should even bother looking. Those stability rules matter for the signal, because location determines temperature and therefore infrared brightness. A planet near A would produce a different thermal signature and dust response than a planet orbiting both stars. A dust belt around one star would heat differently than a belt shared by the binary, because the radiation field is not constant. Even the same dust mass can look dramatically different depending on geometry. Proxima adds another layer, and it is a layer with consequences that extend beyond simple brightness. It is a flare star with intense bursts of radiation, and those flares can change the chemistry of nearby material. Its activity can erode atmospheres and alter photochemistry, and it can also influence dust through stellar wind pressure. Even if Proxima is distant, its presence reminds us that habitability is not only about distance from a star, but also about the star's temperament. The nearest system is therefore paradoxically difficult, and the paradox is the point of this chapter. We can measure it with exquisite precision, but precision exposes complexity, and complexity demands interpretation. Every extra photon reveals another component that must be modelled, subtracted, or explained. At this distance, the system is not a dot, it is a landscape. This is where the documentary's central question takes shape, and where the narrative tightens around a single anomaly. If Webb is seeing extra infrared emission, where is it coming from, and how is it distributed in space? Is it concentrated near one star, spread across the binary, or offset in a way that suggests structure? The answer determines whether we are looking at a local dust cloud, a belt, or a compact object. An asymmetry is especially provocative, because symmetry is what simple models predict when nothing is perturbing the system. Dust disks can be lopsided if planets perturb them, if collisions create temporary clouds, or if stellar radiation pushes grains into arcs. In binaries, even the stars themselves can impose a symmetry by heating one side of a structure more strongly at certain orbital phases. A planet can also appear as a localized warm spot, but only if we can separate it from the star's halo. Here the visuals matter, because the audience needs to feel how subtle the evidence can be. On screen, a bright star is not a clean circle, but a complex pattern of diffraction spikes and faint rings, with a soft glow that fades outward. A tiny excess is not a glowing planet icon, but a slight bump in a radial profile or a faint patch that persists after subtraction. The drama is in the residuals, and the residuals are where mistakes like to hide. The investigation must therefore proceed in layers, and each layer is a filter against self-deception. First, we ask what Webb actually measured, and what the uncertainties allow, including how the point spread function behaves for such bright targets. Then we ask what astrophysical sources can produce that measurement, and whether they are consistent with what we know about the system's age and dynamics. Finally, we ask what those sources imply for planets, habitability, and future missions, because interpretation is only useful if it changes what we do next. We also have to be honest about what could mislead us, because infrared instruments have their own personalities. Infrared detectors can show persistence, where a bright source leaves a fading imprint that contaminates later exposures. Complex point spread functions can create side lobes and diffraction features that look like compact sources. Bright targets can produce ghosts and scattered light paths inside the instrument, and those paths can form arcs or blobs that mimic real emission. The closer and brighter the star, the more careful the analysis must be, and the more conservative the claims must remain. That caution does not weaken the mystery, and it does not drain it of wonder. It sharpens it, because it forces us to define what would count as convincing. If the signal survives the tests, it becomes more meaningful, because it has earned its reality. If it fails, the failure teaches us how to read the nearest stars with the next generation of instruments, and it tells us where our assumptions were too simple. Alpha Centauri is also a cosmology story in miniature, because nearby systems provide boundary conditions for the galaxy. They anchor our models of how planets form, how disks evolve, and how common habitable environments might be, because we can measure stellar properties with high precision. When we know distance well, we know luminosity well, and when we know luminosity well, we can infer temperatures and dust locations more reliably. The nearest neighbour becomes a calibration point for everything farther away. If our nearest neighbour has an unexpectedly bright dust cloud that changes how we interpret infrared surveys of other stars, because dust can masquerade as planets in population studies. If it hides planets behind dust, that warns us about false negatives across the Milky Way, where we might miss worlds simply because their systems are dusty. If it reveals planets through dust structures, that gives us a new detection pathway, one based on the architecture of debris rather than direct planetary light. Each outcome rewrites a small part of our broader inference engine. The same logic scales outward, and it is one of the quiet themes of modern astronomy. Understanding one well-measured system helps calibrate population statistics from thousands of distant stars, where individual details are blurred. It connects the local neighbourhood to the broader question of how often nature builds Earth-like worlds and under what conditions those worlds persist. Alpha Centauri is close enough to be specific, yet representative enough to matter. It also reframes biosignature hopes, because the path to detecting life is paved with false positives and false negatives. If dust and stellar activity can mimic or mask planetary signals here, they can do so everywhere, including around the most promising targets. If we cannot cleanly separate a dust cloud from a planet at 4 light-years, what does that imply for systems 50 or 500 light-years away? The nearest neighbour becomes a stress test for our confidence. So Chapter 1 sets the stage, and it does so with a deliberate unease. Alpha Centauri is close, bright, and constantly in motion, and those traits make it both ideal and treacherous. Webb's infrared sensitivity offers a new way to see what optical light hides, but it also opens new ways to be fooled, because it reveals faint structures that sit at the edge of calibration. The telescope is powerful enough to find subtle truth, and powerful enough to expose subtle error. We are left with a precise, unsettling premise, and it hangs in the air like a question we cannot ignore. The nearest star system should be the easiest to read, yet its infrared story refuses to settle into a tidy model. Something in the data looks warmer, brighter, or more structured than expected, and the system's geometry ensures that every explanation has consequences. Next, we follow the evidence. We break down what Webb observed, how infrared excess is defined, and which physical scenarios can produce a symmetry in a multi-star system. Then we test each explanation against what the nearest neighbour will allow, because in the end, the closest stars do not reward assumptions. They reward patience, and they reward the discipline to admit what we do not yet know. Alpha Centauri feels like a control case, because it is close and familiar in the night sky. Yet the system's core is not one sun, and normal rules bend under a double gravity. In wide shots, it looks serene. Two bright points hanging in the same neighbourhood of space, almost like a paired jewel. In the physics, it is a coupled machine, where every orbit and every photon has a companion influence. Alpha Centauri A and Alpha Centauri B are a gravitational duet, locked into a long, slow dance. They look like the Sun's cousins, but cousins do not guarantee Earth-like outcomes, especially when they share a stage. Alpha Centauri A is a G-type star with near solar mass and temperature, which invites easy comparisons. Its spectrum is Sun-like enough to anchor our expectations, and dangerous enough to mislead them when we forget the binary. A's light is not just bright, it is a measured luminosity that sets the energy budget for any nearby world. That budget determines where liquid water could persist, but it also determines where dust grains heat up and glow. In practice, luminosity is a thermostat written in starlight, and planets read it with their atmospheres. Change the incoming flux a little, and you can shift clouds, ice lines, and even the chemistry that survives in the air. Alpha Centauri B is a K-type star that is cooler, dimmer, and slightly less massive than A. Its gentler light shifts every climate argument inward, and every detection threshold upward, because smaller signals hide more easily in noise. K-type stars are often described as calmer long-term hosts, but calm is a statistical word, not a promise. B's lower luminosity changes the scale of everything: habitable zones, dust temperatures, and the contrast between a planet and its star. Both stars are old enough that any primordial gas disk is long gone, stripped away by time and radiation. What remains should be mature architecture, or debris that signals ongoing grinding in belts and reservoirs. Their ages are often estimated as broadly sun-like, on the order of several billion years, with uncertainties that still matter. That matters because dust should fade with time unless something replenishes it, and replenishment implies active collisions. In other words, a bright infrared glow in an old system is not impossible, but it is suspicious. It invites a question that sounds simple and turns out to be hard. What is still making fresh dust, and why now? Their luminosities set the scale of their habitable zones, which are not single lines but bands with fuzzy edges. A's temperate band sits farther out than B's, and the difference reshapes stability maps for where planets can safely persist. Those habitable zones are usually drawn as circles on diagrams, clean and reassuring. In a binary, those circles are only the first layer, because gravity and extra illumination add time dependence to the climate. Even the colour of the light matters, because spectra tilt toward different wavelengths as stars cool. A slightly warmer star pushes more visible light, while a cooler star leans redder, and atmospheres absorb those colours in different ways. That spectral tilt is not cosmetic because molecules care about wavelength. Ozone, water vapour, and carbon dioxide absorb in specific bands, so the same total energy can drive different photochemistry under different stellar colours. Their activity cycles complicate the word sun-like, because magnetic surfaces are not smooth lamps. Spots, plages, and magnetic variability can mimic planets in radial velocity, especially at the meter-per-second level where Earth-like signals live. When a dark star spot rotates into view, it distorts spectral lines and shifts the apparent stellar velocity. The shift is not a true wobble from a planet, but the instrument cannot know that without careful modelling. The effect is subtle but relentless, because it is tied to rotation and evolving magnetism. A star can change its own apparent velocity by reshaping its surface brightness, and the pattern can drift as spots emerge and decay. In a nearby system, we can measure stellar properties with unusual precision, from effective temperatures to radii and metallicities. precision does not simplify the story, because it exposes every second-order effect we usually ignore at greater distances. We can resolve subtle line asymmetries, tiny photometric variations, and even the way convection patterns imprint on spectra. Each improvement is a gift, and each gift reveals another way the star can impersonate a planet. Granulation, for example, is a boiling pattern of rising hot gas and sinking cool gas, and it shifts line shapes by tiny amounts. Those shifts average out imperfectly, and the leftovers can sit right where a small planet would hide. At the same time, convection is not uniform across a stellar disk, so the imbalance changes with viewing geometry. As the star rotates, different convective patches dominate the light, and the spectral centroid can drift without any planet at all. Now we add the binary itself, which is the chapter's real antagonist, because it never stops acting. Two stars mean time-dependent gravity and time-dependent heating, even before planets enter the frame. A and B orbit a shared centre of mass in roughly 80 years, a timescale long enough to feel geological. Their path is elliptical, so their separation changes across decades, and the system's background conditions never stay fixed. In visuals, that orbit is a slow tightening and loosening, like a breath taken over a human lifetime. The stars swing closer, then drift apart again, and every intermediate distance rewrites the gravitational math. At wide separation, the pair can be tens of astronomical units apart, like a distant companion in the outer solar system. At closer approach, the gravitational crosstalk becomes stronger and more disruptive, and the safe real estate shrinks. That changing separation is not a footnote, because disks and planets integrate perturbations over time. A stable orbit must survive not one configuration, but all of them, wide, close, and every intermediate geometry. Binary dynamics carve space into allowed zones and forbidden zones, and the carving is mathematical rather than intuitive. The boundaries are not sharp walls, but regions where eccentricities grow and orbits unravel, sometimes slowly and then suddenly. A planet can look stable for thousands of orbits and still be doomed, because small kicks accumulate. In celestial mechanics, the danger is often not a single shove, but a steady rhythm that keeps pushing at the same phase. This is resonance in its most practical form, a repeated gravitational nudge that lands on the same beat. When the beat matches an orbital period ratio, energy can be pumped into eccentricity like a swing pushed at the right moment. In simulations, the fingerprints of resonance show up as narrow bands of instability, like cracks in otherwise calm ice. Step across one of those bands, and an orbit that looked ordinary can become chaotic over long times. There are two basic planet options in a binary like this, and they lead to different architectures. Planets can orbit one star, or orbit both stars as circumbinary worlds, and each choice comes with a stability price. Circumstellar planets must stay close enough to their host star to avoid the companion's repeated tugs. The safe region shrinks when the binary is tighter, and it can also shrink when the planet's orbit becomes even slightly eccentric. That safe region is sometimes described as a fraction of the binary separation, but the fraction is not universal. It depends on the binary's eccentricity, the mass ratio, and the way resonances overlap as the system evolves. Circumbinary planets must stay far enough out that the binary acts like a single mass, at least on average. Too close, and resonances pump eccentricity until the orbit breaks, turning a planet's path into a chaotic wandering. These stability rules are not abstract because they predict where dust can persist and where it is constantly stirred. Dust grains trace gravitational structure faster than planets do, and they glow so they become our visible ink. Resonances can trap dust into rings, arcs, and clumps, like traffic patterns shaped by invisible lanes. Close passages can clear gaps, excite collisions, and feed new dust into the infrared, briefly turning the system into a beacon. In a single star system, a gap can suggest a planet, because planets carve lanes as they orbit. In a binary, a gap can be the binary's rhythm, and the planet interpretation becomes fragile without extra evidence. This is where the phrase sun-like becomes a trap, because it tempts us to import solar system intuition. The stars can resemble the sun in isolation, while the environment behaves unlike the solar system, with two gravitational centers writing the rules. Planet formation is also harder in a binary, because early planetesimals collide faster when their orbits are stirred. Higher collision speeds can grind material down instead of building it up, turning growth into erosion. In the earlier stages, dust grains must stick, then become pebbles, then become kilometre-scale bodies. If the binary pumps relative velocities too high, those gentle mergers become destructive impacts, and the pathway to planets narrows. The key issue is relative speed, because gravity helps only when impacts are slow enough to merge. When impacts are too fast, bodies shatter, and the system produces dust more efficiently than it produces planets. That collision physics has a threshold character. Below a certain speed, rocks can accrete. Above it, they fragment. In a binary, the threshold can be crossed repeatedly as forced eccentricities rise and fall with the companion's pull. Some models still allow terrestrial planets around A or B, but the conditions are narrower and more conditional. The disk must be calm enough, and the stable zone must be respected, and the timing of growth must outrun the stirring. Even if planets form, long-term survival is not guaranteed, because stability is a billion-year requirement. A small eccentricity increase can shift climate forcing, and repeated forcing can erase stability, even without a dramatic orbital ejection. Habitability starts with energy balance, and energy balance starts with luminosity and distance. A's higher luminosity moves its habitable zone outward, while B's pulls it inward, changing where oceans could persist on a rocky surface. But habitability also depends on orbital stability over billions of years, not just a snapshot in time. Biosignatures require persistence, not just a momentary temperate orbit that lasts a few million years and then destabilizes. Binary forcing can modulate a planet's eccentricity and obliquity, and those parameters matter for climate. Those changes can drive climate cycles that are stronger than Earth's Milankovitch variations, potentially pushing a world between extremes. On Earth, small orbital changes pace ice ages, but they do not usually sterilize the planet. In a binary, the amplitude can be larger, and the timescales can be tuned by resonances that keep returning like a drumbeat. A planet around A might see B as a bright moving star in its sky, shifting position over years and decades. That extra light is usually small, but its variability can still matter for climate models, especially near the edges of habitability. Imagine a night sky where the second star slowly brightens as the binary closes, then fades as it opens again. Even if the total energy change is modest, the seasonal and spectral character of that light can alter atmospheric chemistry. The added illumination is also directional, arriving from a moving point that changes phase with the orbit. Over decades, that moving lamp can shift which hemisphere receives extra twilight and how photochemistry cycles through time. That slow modulation raises a quiet question. Would biology adapt to a sky with a second, wandering sunrise, or would it treat it like a long, faint season? In a stable climate, subtle forcing can still matter if it is persistent. A planet around B faces a different balance because B is dimmer and cooler, and the habitable zone is closer in. The habitable zone is closer in, where tidal effects and activity concerns rise, and where observational signals are more compact. Closer in orbits can mean faster years, stronger tidal interactions, and different rotation states over long times. None of these factors automatically forbid habitability, but each one adds another term to the equation we must carry. Tides can damp eccentricity and stabilize climates, but they can also lock rotation and reshape atmospheric circulation. A world with a permanent day side and night side is not doomed, yet it must solve heat transport differently. The chapter's tension is that habitability and detectability are linked, and the link is cruel. The most interesting orbits are also the hardest to confirm in a bright binary, where stellar physics competes with planetary signals. Radial velocity is powerful, but Alpha Centauri is a difficult target even for the best spectrographs. Stellar activity adds signals that can masquerade as planets, or bury them, and the binary adds a moving background of blended light. Spots rotating across the stellar surface distort spectral lines, changing their shapes rather than shifting them cleanly. That distortion can look like a periodic wobble, and it can drift as activity evolves, breaking the neat periodicity we crave. The binary companion adds contamination through blended light and changing line profiles, especially when the stars are close on the sky. Even small leakage between A and B can bias precision measurements, because the contaminant spectrum is not constant. In practice, observers must model not only the target star, but the neighbour's contribution and its time variation. The challenge is not simply more noise, it is structured noise that can mimic exactly what we are searching for. Even the barycentric motion of the stars matters, because their orbital velocities change slowly with the 80-year period. That long trend must be removed cleanly, or it can warp the residuals where small planets would appear. And because the system is so bright, even tiny instrumental drifts become visible in the data. What would be negligible elsewhere becomes decisive here, an advantage for calibration and a trap for overconfident interpretation. Transit searches face a different obstacle, which is geometry and alignment. The probability that an Earth-like orbit transits is low, even in the nearer system, because the orbital plane must line up with our line of sight. A non-detection in transits is not very informative, because most planets do not transit. Yet a detection would be transformative, because it would give radius, orbital period, and a clean clock to compare against other methods. Direct imaging faces the most obvious obstacle, which is glare and diffraction. Too bright stars create complex diffraction patterns that complicate subtraction and contrast, and the patterns shift with pointing, wavelength, and optics. In visual terms, it is like trying to photograph a firefly next to a pair of floodlights, while the camera lens creates rings and spikes. Even a perfect telescope must fight physics, because light is a wave and it spreads. Those diffraction rings are not just pretty artifacts, they are structured light that can hide faint sources. When you subtract the star, you are subtracting a pattern, and any mismatch leaves a ghost that looks astrophysical. These detection limits matter for interpretation, because dust can be easier to see than planets in the infrared. Dust is not only a byproduct, it is a competing explanation, and sometimes it is the dominant one. This is where infrared astronomy becomes the key language. Webb sees heat, and heat can come from dust, planets, or instrument behavior, so the interpretation must be disciplined. Warm dust emits strongly in the mid-infrared, where temperatures of a few hundred Kelvin glow efficiently. The peak wavelength depends on temperature, and temperature depends on distance and grain properties, including how well grains absorb and re-radiate. Real grains are not perfect blackbodies, and that detail matters when we translate colour into distance. Small grains can run hotter than expected because they radiate inefficiently at long wavelengths, so warm does not always mean close. Grain composition matters too, because silicates, carbon-rich grains, and icy mixtures absorb differently across the infrared. The same temperature can produce subtly different spectral slopes, and those slopes become clues when the data are good enough. A small amount of dust close to a star can outshine a small planet in infrared, because dust has enormous collective surface area. That is why an infrared excess is both exciting and ambiguous, a signal that begs for context. An infrared excess means the system is brighter than the stellar photosphere predicts at those wavelengths. The baseline is a stellar model, and the deviation is the clue, but the clue is only as good as the calibration. For nearby bright stars, calibration is both easier and harder. Easier because the signal is strong, harder because detectors can saturate and optics can scatter. The brightest targets can stress instruments in ways that faint targets never do. If the excess is smooth and symmetric, a debris disk is a natural explanation, because many disks form broad belts. If it is compact or offset, the story becomes more complicated, because asymmetry implies dynamics or transient events. A debris disk is not a protoplanetary disk, and the distinction matters for interpretation and timescales. Debris disks are second-generation dust, replenished by collisions and comet activity, because small grains are removed relatively quickly. Radiation pressure can push the tiniest grains outward, while pointing, Robertson drag, can cause others to spiral inward over time. In plain language, dust does not last long on its own, so a bright dust signal implies a source. In a system like this, the removal clock can be short compared with the system's age, which is the heart of the puzzle. If we see warm dust now, something must be feeding it now, or we are catching a rare moment. To distinguish dust from a planet, we need more than brightness, because brightness alone can be deceptive. We need spectral shape, spatial structure, and repeatability across epochs, and we need them to agree rather than contradict. Spectral shape can reveal grain temperatures and compositions, because silicates and other materials leave broad features in the mid-infrared. A planet's spectrum can differ, but only if signal-to-noise and calibration cooperate at the needed precision. Spatial structure can reveal rings, belts, or asymmetries, which are the fingerprints of gravitational sculpting. A planet should behave like a point source, while dust often spreads or forms arcs, though limited resolution can blur the difference. Repeatability is the discipline that protects us from artifacts, especially in a system this bright. A real structure should persist or evolve predictably, not appear only in one reduction, one roll angle or one particular subtraction method, binary systems add a special twist, because dust can be circumstellar or circumbinary, and the same excess can map to different distances. The same infrared excess can mean very different architectures, depending on which star heats the grains. If the dust is circumstellar around A, it traces A's stable zone and collision environment, which are shaped by B's periodic tug. If it is around B, the temperature and scale shift and the same observed wavelength implies different grain locations. If the dust is circumbinary, it wraps both stars and feels their combined gravity, like a belt around a double lantern. The heating becomes phase-dependent, and the structure can be sculpted into patterns that change subtly with the binary's orbit. The circumbinary belt can also masquerade as two separate features, because projection and illumination can create apparent peaks. Brightness peaks can align with viewing geometry rather than with physical clumps, which is why images must be interpreted cautiously. This is why Webb's hints feel strange rather than definitive, even when the data are carefully taken. The system can generate misleading signatures even when nothing exotic is present, because binaries naturally create complexity. The most provocative case is asymmetric warm dust, because asymmetry implies a driver and a timescale. The driver could be a recent collision, comet delivery, or a planet shepherding material, and each option leaves a different kind of footprint. A recent collision can create a localized cloud of fine grains, like a smoke plume in orbit. Fine grains radiate efficiently, and the cloud can fade as grains are removed, so a transient excess might be a snapshot of a brief event. If the collision involves large bodies, the aftermath can include a cascade of fragments that keeps producing dust. The infrared brightness can then decline over years to decades, offering a measurable clock if we return and look again. Comet delivery can also create warm dust, especially if reservoirs are perturbed inward from colder regions. In a binary, perturbations can be periodic and cumulative, nudging small bodies onto star-grazing paths that shed dust as they heat. Those infalling bodies can behave like a slow drizzle or a sudden storm, depending on how resonances sweep through their orbits. If Webb is seeing warmth near the star, we have to ask what is feeding the furnace. A planet can shepherd dust into resonant clumps, like a slow gravitational rake gathering grains into preferred longitudes. The clumps can look like a compact source if resolution is limited, and they can persist as long as the resonance holds. But the binary itself can also create lopsided patterns, even without any planet at all. Time-varying gravity can trap dust in stable islands, and clear other regions, producing symmetries that are dynamical rather than planetary. This is the interpretive cliff edge. The same pattern can be read as a planet, or as the binary's own signature. The only way forward is to ask what each scenario predicts next, and then test those predictions. The chapter's job is to teach the audience what Webb can and cannot claim, without dulling the mystery. An excess is not a planet, and a clump is not proof, because astrophysical ambiguity is the default state. We also need to remember how bright stars stress instruments, even instruments as carefully designed as Webb. Webb's point-to-spread function has rings and spikes, and subtraction leaves residual structure that can resemble faint extended emission. Detector effects can imprint false features, especially near saturation limits where pixels respond non-linearly. Persistence and scattered light can create faint ghosts that mimic real emission, and those ghosts can survive naive processing. So the analysis must separate astrophysics from optics, which is a technical way of saying separate the sky from the telescope. The same data can look different under different processing, and that difference must be mapped and understood. Observers use roll angles, reference stars, and forward modelling to test whether a feature rotates with the sky or stays fixed to the instrument. If it stays fixed, it is probably optics. If it rotates, it becomes a candidate for reality. That workflow is slow by design, because it forces humility into the pipeline. When a claim depends on subtraction, the subtraction itself becomes an experiment, and every assumption must be challenged in daylight. Historical context matters here, because Alpha Centauri has a record of near discoveries and near misses. Claims have risen and fallen as methods improved and systematics were found, and each episode has trained the community's skepticism. For decades, the system has been a proving ground for precision techniques, from early astrometry to modern radial velocity. The temptation is always the same. If any nearby star should yield a planet, surely it is this one. Even the name carries that cultural weight, because it sits in our stories as the nearest other sun. That familiarity can bias us, and it can also sharpen us, because the community knows how easily hope can outrun data. That history does not mean new hints are wrong, and it does not mean the system is empty. It means the bar for confidence is higher, and the language must be careful, because the cost of self-deception rises with excitement. The deeper point is that the nearest neighbour is a calibration target in the scientific sense, not just a cultural icon. If we cannot interpret dust and activity here, our inferences elsewhere become less secure because we lose a benchmark. A surprising dust environment around A or B would ripple outward into mission planning and strategy. It would change how we plan direct imaging, and how we estimate exozodiacal noise, which can drown out faint planets like a fog. It would also change how we interpret biosignature prospects, because dust can hide planets and complicate spectra. Activity can mimic atmospheric signals in future spectroscopy, and dust can add extra continuum light that dilutes absorption features. At the same time, dust can be a map rather than a nuisance, because it responds quickly to gravity. If dust is being shepherded, it can reveal planets indirectly, even when the planets remain invisible behind glare and noise. So the binary is not just a complication, it is a diagnostic tool if we learn to read it. Its gravity sculpts material in ways that encode the system's architecture, and those encoded patterns can be compared against dynamical models. We return to the central question with sharper definitions and a narrower set of possibilities. What exactly is strange in Webb's infrared view, and which physical scenario survives the constraints of stability, temperature, and repeatability? If the excess belongs to A, it implies warm material in A's inner system, close enough to be hot in mid-infrared. That would raise questions about replenishment, because old systems usually do not keep large amounts of warm dust without ongoing collisions. If it belongs to B, it implies a different temperature and dust location, because B's lower luminosity heats grains less at the same distance. The same observed colour could then mean dust that sits closer in, where the binary's perturbations may be stronger. If it is circumbinary, it implies a belt that spans both stars' influence, with heating that depends on orbital phase. That would reshape our assumptions about stability and replenishment, because the belt would live in a region shaped by combined gravity. Each option has consequences for planet formation and habitability, because dust traces where collisions happen and where bodies survive. Each option also has consequences for how we search, because it changes where noise lives and what wavelengths are most informative. A circumstellar dust cloud might suggest active inner belts that complicate direct imaging near the habitable zone. A circumbinary belt might push the dust farther out, changing the contrast problem but raising questions about how material is transported inward. The chapter ends with a controlled suspense, not a conclusion, because the evidence is suggestive but not final. Webb has given a clue that could be dust, a planet, or a trick of light, and the system is skilled at producing all three illusions. Next, we follow the evidence into Webb's measurements and models. We test whether the infrared signature holds up, and what structure it truly implies, because only repeated, consistent constraints can turn a hint into a discovery. We pivot away from the bright binary and toward the system's wildcard. Alpha Centauri A and B glow like familiar suns, steady and inviting, yet our attention slides outward to a faint ember. Proxima Centauri is smaller, cooler, and dimmer than A and B, and the camera almost has to search for it. In wide shots it looks like an afterthought, an extra point of light drifting far from the pair. Yet it dominates the story of nearby habitability because it is close. It is close to us, and its habitable zone is close to it, tucked in tight like a ring around a coal. Proxima is a red dwarf, an M-type star with low mass and low luminosity. Its surface temperature is thousands of degrees cooler than the Sun's, so its light shifts toward deep reds and near-infrared. In visual terms, it is a star that hides in plain sight, bright in the wavelengths our eyes do not favour. That faintness is not a minor detail because luminosity sets the scale of everything around it. A planet must orbit near Proxima to receive the same average energy Earth gets from the Sun. The result is a compact system where days are short, years are brief, and the star looms large in the sky. Inside, Proxima burns fuel slowly, so its lifetime stretches into trillions of years. The physics is simple but profound. With less mass, the core runs cooler, and nuclear fusion proceeds at a gentler pace. The star sips hydrogen rather than guzzling it, and it can keep shining long after larger stars have faded into remnants. That longevity changes the odds, because time is a resource for biology. A small star can offer stable energy for longer than the universe has existed, if it can also offer stability in the right ways. Red dwarfs dominate the galaxy by sheer numbers. Most stars in the Milky Way are M dwarfs, faint and common, scattered through the spiral arms like grains of dark sand. Their prevalence is one reason exoplanet catalogues are so full of short-period worlds. It is easier to find planets around small stars, and there are simply more small stars to search. If life is even moderately possible around them, they dominate the statistics. The cosmological lottery is weighted towards small, cool stars, and Proxima is our nearest ticket. There is also a historical twist to Proxima's importance. It was identified in the early 20th century as a companion to the Alpha Centauri System, and its very name, Proxima, means nearest. For decades it was a quiet footnote, a dim neighbour beyond the bright pair, interesting mostly because it was close. Modern exoplanet science turned that footnote into a headline. When our instruments became precise enough to detect tiny wobbles in starlight, Proxima stopped being a faint companion and became a laboratory. But Proxima is not a quiet example of its class. It is magnetically active, and its activity is not subtle. It flares, it spits plasma, and it floods nearby space with high-energy radiation. When the star erupts, the scene changes from calm infrared glow to violent flashes in ultraviolet and X-rays. The same star that hides planets in dim light can also punish them. That duality, promise and peril in the same object, is the chapter's engine. To understand why, we have to explain how a red dwarf makes a magnetic field. Inside Proxima, hot plasma moves and conducts electricity, and that moving charge generates magnetism. Convection churns the interior like a boiling pot, carrying heat outward through rising and sinking flows. Rotation then organizes that motion, twisting it into patterns that can amplify magnetic fields. In many red dwarfs, the interior can be largely convective, without the layered structure that shapes the Sun's dynamo. The result can be more chaotic than the Sun's, stronger in places, less predictable in time. Magnetic field lines are not just abstract curves in a diagram. They are real structures in plasma, storing energy as they twist and tangle. The star's surface becomes a landscape of active regions, where fields emerge, reconnect, and snap into new configurations. Energy accumulates gradually, then releases abruptly. That release is what we call a flare, and it is as much a magnetic event as a luminous one. In visual terms, it's a sudden brightening that can outshine the star's normal output for minutes. A flare is a multi-wavelength event. The star brightens in optical light, and even small telescopes can catch the jump as a sharp spike in a light curve. But the danger is often in UV and X-rays, where the photons carry enough energy to break molecular bonds. Those photons ionize upper atmospheres, creating layers of charged particles that behave differently than neutral air. They also change chemistry faster than climate can respond, pushing atmospheres into states that would never occur under steady sunlight. If Earth's atmosphere is a slow chemical machine, a flare is a wrench thrown into the gears. Coronal mass ejections add a second threat, because they carry particles and magnetic fields. A CME is a cloud of magnetized plasma launched into space, and it can arrive like a storm front. When it hits a planet, it can compress the magnetosphere, forcing the protective boundary closer to the surface. It can also drive currents in the upper atmosphere, heating it and increasing escape. If the planet lacks a strong magnetic shield, the wind can strip it directly. Over long time, that stripping can remove oceans by removing hydrogen, leaving oxygen behind to react with rocks. The details matter, because atmospheric loss is not a single mechanism. High-energy photons can heat the upper atmosphere until it expands, and the expanded gas becomes easier to erode. Ion pickup can carry away charged particles along magnetic field lines, especially when stellar wind pressure is high. Sputtering can knock atoms into space, one collision at a time, like sandblasting. Each process depends on the planet's gravity, composition, and magnetic environment, and each process is amplified by closeness. Around Proxima, closeness is unavoidable. This is the chapter's core tension. Proxima's low luminosity makes its habitable zone tight and close in, a narrow band where a world can be temperate in average energy. That makes temperate orbits easier to detect because periods are short and signals repeat quickly. A planet tugs the star more noticeably when the star is small, and it transits more often when its orbit is compact, yet the same closeness increases exposure to flares and stellar wind. The habitable zone is also the danger zone. The habitable zone around Proxima is compressed into a narrow ring near the star. A planet there receives Earth-like average energy, but from a star that behaves differently. The spectrum is redder, which changes how energy is absorbed by ice, water, and land. Ice can be less reflective under red light, which can shift climate feedbacks in subtle ways. Meanwhile, the UV comes in bursts rather than steady drizzle, so photochemistry becomes episodic. Climate and chemistry must adapt to a pulsed environment where calm days are punctuated by radiation storms. Close-in orbits also raise tides, and tides reshape rotation. The gravitational pull varies across a planet's body, stretching it and dissipating energy as heat. Over time, that dissipation can slow rotation and lock a world into a stable spin state. Many Proxima habitable planets are likely tidally locked or trapped in resonances, depending on their eccentricity and interior structure. One hemisphere can face perpetual day, and the other can face perpetual night. That geometry can create extreme temperature gradients, especially if the atmosphere is thin. Tidal locking is not an automatic death sentence, but it changes the problem. The intuitive fear is a frozen night side and a scorched day side, a world split into two climates that cannot reconcile. Yet atmospheres are mobile and winds can transport heat if there is enough air to move. If an atmosphere is thick enough, circulation can carry warmth to the night side and keep gases from freezing out. If oceans exist, currents can move energy as well, smoothing extremes over long timescales. A stable terminator region can exist, where day and night meet in persistent twilight, an annulus of habitable compromise. But the same close orbit that enables heat transport also concentrates radiation risk. High-energy photons hit the day side repeatedly, and energetic particles can reach both hemispheres through atmospheric circulation and magnetic connections. A thin atmosphere can collapse on the night side, freezing out gases and shrinking the pressure until liquid water becomes impossible. A thick atmosphere can survive, but it must survive erosion first, and it must survive long enough for climate to settle. Habitability becomes less like a static label and more like a dynamic contest. This is where habitability becomes an engineering question for nature. Can a planet replenish its atmosphere through volcanism and outgassing, replacing what is lost to space? Can it retain water against photodissociation and escape, keeping hydrogen from streaming away? Can it sustain a magnetic field long enough to matter, or does its core cool too quickly? Each answer depends on interior heat, composition, and history. Even the presence of continents can matter, because weathering can draw down greenhouse gases and reshape climate. Proxima's early life likely matters more than its present. Red dwarfs can be brighter and more active in their youth, especially in high energy output, even if their visible light is modest. That means the habitable zone migrates inward as the star settles and dims in bolometric terms. A planet now in the temperate zone may have endured a long runaway greenhouse phase, with oceans evaporated into steam. In that phase, water vapor becomes a powerful greenhouse gas, raising temperatures further and accelerating loss. The upper atmosphere fills with hydrogen from dissociated water, and hydrogen escapes easily into space. That early era is a kind of planetary trial by fire, and it may last hundreds of millions of years. On Earth, life emerged relatively early, but Earth did not face the same prolonged high-energy environment at such close orbital distances. Around Proxima, a world might need deep reservoirs, rapid cooling, or unusual chemistry to keep water. It might also need to form late, after the most violent youth has passed, or to migrate inward from farther out. These are not convenient loopholes, but they are real possibilities that shape our expectations. So Proxima becomes the most promising and most perilous target at once. It is promising because small stars make small habitable zones, with frequent transits and strong radial velocity signals. It is perilous because activity can sterilize surfaces and erase atmospheres, especially early on. The same physics that helps detection can sabotage life. That contradiction is why Proxima feels like a riddle rather than a destination. Now we connect this to the documentary's central question about strange infrared signals. Proxima is faint in visible light, so infrared contrast can be favorable, and that is where modern observatories excel. A cool star emits more of its energy in the infrared, shifting the balance of what bright means. That shift aligns with the strengths of the James Webb Space Telescope, which is built to see heat and molecules. In a sense, Webb is tuned to the wavelengths where Proxima speaks most clearly. Infrared relevance is not just about brightness, it is about temperature differences. A rocky planet warm to a few hundred Kelvin emits thermal radiation in mid-infrared bands, and that emission can carry the imprint of its atmosphere. The day side of a tidally locked world can glow differently than the night side, creating phase variations as it orbits. Dust heated by Proxima can glow as well, sometimes more brightly than the planet, because dust can present a large collective surface area. Around a dim star, even modest warm dust can be conspicuous, like smoke lit by a small fire. JWST can also search for atmospheric molecules if geometry cooperates. If a planet transits, Webb can measure transmission spectra through the limb, watching starlight filter through a thin ring of atmosphere. In that filtered light, molecules imprint absorption features, and those features can reveal composition and temperature structure. If it does not transit, emission or phase curves might still be possible in special cases, especially if the planet is warm and the system is favourable. Even non-detections can constrain haze, clouds, and mean molecular weight, because a flat spectrum is information too. But Proxima's activity complicates every measurement. Flares change the star's brightness and spectrum on short timescales, and the changes are not always smooth. A flare can add extra UV that drives new chemistry, and it can add extra infrared through heated regions and recombination processes. These events can inject time-dependent signals into light curves and spectra, creating apparent features that are not planetary. They can also heat dust transiently, creating afterglows that look like excess emission. The data can become a moving target while we're trying to measure it. This is the observational paradox of red dwarfs in one sentence. Close-in planets are easier to find, but flare noise makes their signals harder to interpret. The star helps by amplifying the planet's gravitational and transit signatures because the star is small and easily perturbed. The star hurts by adding structured variability that imitates those signatures, sometimes with uncanny precision. In practice, discovery becomes a contest between repeating orbital patterns and evolving stellar behavior. Radial velocity is especially vulnerable to this imitation. The method relies on measuring tiny shifts in spectral lines, interpreting them as motion toward and away from us. Stellar spots and plages distort those lines because they change the brightness pattern across the rotating surface. As the star spins, the distorted pattern creates apparent Doppler shifts that can look like a planet. On an active M dwarf, those shifts can be comparable to a small planet's signal, and sometimes larger. The instrument may be precise, yet the star itself becomes the dominant source of uncertainty. Even worse, activity can be quasi-periodic rather than cleanly periodic. Spots evolve, migrate, and appear at different latitudes, and differential rotation can change their apparent period. The resulting signal can drift in phase and amplitude, producing a wobble that is almost consistent with an orbit. A planet signal can hide inside that drift, or be falsely extracted from it depending on modelling choices. This is not just a technical nuisance, it shapes what we think exists. Observers fight back with diagnostics that track activity. They monitor chromospheric lines that brighten when magnetic regions are active, and they watch photometric variability that reveals rotating spots. They analyse line shape indicators that can separate true motion from surface distortion, and they compare signals across wavelengths. They model correlated noise with statistical tools designed for messy data, and they test whether a signal remains stable across observing seasons. But the fight is never perfect, and Proxima is an expert at ambiguity. In the data, it can look like several planets at once, or like none. That ambiguity matters because Proxima already has a planet that changed the conversation. Proxima B was announced as a roughly Earth-mass world in a temperate orbit, detected through radial velocity after careful monitoring. Its period is about 11 days, which places it in the compressed habitable zone. It became the nearest potentially habitable exoplanet we know, and that proximity reshaped priorities overnight. A world that had once been science fiction suddenly had an orbital period, a minimum mass, and a place on a plot. In visual terms, the discovery is often shown as a simple curve, starlight shifting back and forth, yet the curve hides years of work. It also hides the fact that Earth mass is not Earth-like. Proxima B's mass suggests a rocky world, but mass alone does not reveal atmosphere. It could be an airless rock with a battered surface, a water-rich world with high-pressure ice, or a planet with a thick secondary atmosphere rebuilt after early loss. It might even have a composition that changes its radius and density in unexpected ways. Proxima B is also a case study in the chapter's tension. Its orbit is close enough for tides and flares to matter, and close enough that the star's wind environment is intense. If it is tidally locked, its climate depends on atmospheric circulation in a way Earth's does not. If it has an atmosphere, that atmosphere is continuously tested by bursts of UV and X-rays. If it lacks an atmosphere, its surface becomes a direct record of radiation and impacts. Either way, it is a world shaped by its star's personality. Later analyses introduced additional candidates and controversy. Proxima C was proposed as a longer period companion, likely more massive and farther out, and the claim sparked immediate interest. A more distant planet could interact with debris, sculpt dust, and hint at a more complex system. Yet the signal sits near the edge of detectability, where sampling and stellar behavior can mislead. Other signals have appeared and faded as datasets changed and as methods improved. The system has become a laboratory for how activity and sparse sampling create false planets, and for how careful observers try to avoid being fooled. This is where Webb enters as both a solution and a new source of confusion. Webb does not measure radial velocity, but it measures infrared light and spectra with extraordinary sensitivity. That can help separate thermal emission from stellar line distortions, because it is a different kind of measurement. Yet infrared is also where dust and flare afterglows can hide, and where a cool star's variability can still matter. Webb can clarify one ambiguity while exposing another. If a planet transits, Webb can look for water vapor, carbon dioxide, methane, and other molecules. It can also detect featureless spectra that imply high clouds or photochemical haze, because haze can mute absorption features across wide bands. Around an active red dwarf, haze formation can be enhanced by UV bursts, which drive complex organic chemistry in upper atmospheres. A flat spectrum can mean an atmosphere is present but masked, and that is a subtle but important distinction. The absence of features is not the absence of air. If a planet does not transit, Webb can still search for indirect signatures. Warm dust belts can be inferred through excess emission, and in rare cases spatial structure can be teased out with careful analysis. A planet can sculpt dust into resonant clumps that shift with orbital phase, like a fingerprint of gravity. But Proxima's flares can also create transient heating that mimics clumps, brightening dust unevenly for a short time. The same infrared glow that suggests architecture can also be a momentary flare echo. This is the chapter's escalation of mystery, tied directly to the central question. If JWST sees anomalous infrared emission near Proxima, what is it? What physical object or process is actually producing those photons? Is it a transient flare afterglow that fades on hours or days, leaving a signature that depends on timing? Is it hot dust from impacts, replenished by collisions in a hidden belt, glowing like fresh ash? Or is it something orbiting that we have not confirmed, repeating with a rhythm that only appears after many observations? Each explanation has a different prediction, and the predictions guide the investigation. A flare afterglow should correlate with high energy activity and decay quickly, with brightness dropping as the plasma cools. Hot dust from an impact should persist longer and show a thermal spectrum consistent with grains of a particular size distribution. An orbiting body should repeat with orbital phase and maintain a stable position relative to the star, aside from expected orbital motion. The mystery is not solved by imagination, but by patterns. We also have to consider the environment between Proxima and the binary. Proxima is bound to A and B, but it lives far away, separated by thousands of astronomical units. In a visual map, it sits on the outskirts, like a distant outpost, rather than a close companion. Its local debris could be independent, formed from its own protoplanetary disk, or it could be influenced by the system's broader gravitational history. Long-period interactions can perturb comet reservoirs and trigger inward delivery, even if the timescales are enormous. That delivery can create dust and confuse infrared measurements, especially if collisions spike episodically. Dust is not just a nuisance in the infrared. In many systems, dust is a tracer of unseen bodies, because it must be replenished to remain visible. Small grains are pushed by radiation forces and stellar wind, and they are ground down by collisions. If we see warm dust near Proxima, it implies ongoing processes, not a static relic. The question becomes whether those processes are steady, like a slow cascade, or sudden, like an impact. A sudden event would have a time signature, and time is something we can measure. Proxima's faintness makes background contamination another risk. In crowded infrared fields, distant galaxies can masquerade as compact sources, and their colours can mimic warm dust. A single image can be deceptive, because the universe is full of faint infrared objects. Proper motion helps separate them, because Proxima moves against the background over months and years. A real companion shares that motion, while a background source stays fixed. In the sky, motion becomes a kind of truth test, so the method becomes a sequence of tests rather than a single image. We compare epochs to see whether emission moves with Proxima and whether it maintains the same separation in angular terms. We compare wavelengths to see whether the spectrum matches dust, rock, or instrument artifacts, because each has a different slope and set of features. We compare timing to flare monitors to see whether the signal tracks stellar outbursts and whether it appears only after high-energy events. We also compare data reductions, because subtle processing choices can create or erase faint structures. This is also where the documentary's tone deepens. Proxima is close enough to tempt us with a simple story, the kind of story we tell about a nearest Earth. It is also active enough to make every story unstable, because the star refuses to be a steady lamp. The star can change its own infrared environment while we are watching, and that means our interpretations must be time-aware. In a system like this, a snapshot is not a portrait, it is a frame from a moving film. The habitability implications remain central, because the audience needs stakes beyond detection. If Proxima B has an atmosphere, it must be resilient or continuously replenished, and that implies active geology or substantial reservoirs. If it has water, it must be protected from escape or stored in reservoirs that can survive long hostile epochs. If it has life, that life must endure radiation regimes unlike Earth's, perhaps with different repair mechanisms or different ecological niches. The question is not only whether life can begin, but whether it can persist. Some scenarios keep hope alive without ignoring the violence. A thick atmosphere can absorb UV and spread heat, and it can also provide a larger column of material to erode before the surface is exposed. A global ocean can buffer temperature swings and dissolve gases, acting as both thermal and chemical storage. A magnetic field can reduce particle stripping, even if it cannot block all radiation, and it can shape where energetic particles deposit their energy. Subsurface habitats can exist even when surfaces are harsh, because rock and water are excellent shields. On such a world, the habitable zone might be measured in meters below ground rather than kilometers above it. Other scenarios are bleak but informative. A planet can be stripped to a bare rock, leaving only a thin exosphere that appears and disappears with stellar activity. It can lose water and become a dry, oxidized world with abiotic oxygen, produced when hydrogen escapes and oxygen remains. That oxygen can mimic a biosignature in spectra if we are careless, because oxygen feels like life to human intuition. Proxima forces us to learn the difference between biology and photochemistry. It forces us to ask what a false positive really means in a violent environment. That lesson loops back to Webb and to infrared interpretation. Infrared spectra can show CO2 bands, water features, and methane signatures, and those features can be tempting to interpret as climate and life. They can also show disequilibrium patterns that suggest active sources and sinks. Around an active star, photochemistry can push atmospheres into strange states without biology, producing hazes and unexpected ratios. A molecule is not a verdict, and a spectrum is not a confession. The context of the star is part of the measurement, so Proxima becomes a warning label for the entire search. The nearest potentially habitable planet might also be the easiest place to generate false positives, because activity can create spurious molecules and dust can dilute or mimic spectral features. The closest target can be the most deceptive, precisely because we can observe it so closely. Proxima teaches us humility at the same time it offers opportunity. It is a nearby system that behaves like a stress test for our methods. Next, we follow the evidence from general physics to specific candidates. We map what is known about Proxima B's orbit and irradiation, and we translate those numbers into physical conditions. We track how flare statistics translate into atmospheric loss rates, and which assumptions dominate the uncertainty. We define what Webb would need to see to claim molecules rather than noise, and what time coverage would be required to rule out transient contamination. The goal is not to be optimistic or pessimistic, but to be disciplined. We also set up the chapter's practical question about the strange infrared signal. If the anomaly is near Proxima, it could be a planet's thermal glow, modulated by phase and weather. It could be warm dust in a belt we have not resolved, glowing steadily or in bursts after collisions. It could be a transient artifact of a flare that happened during the observation, leaving a fading infrared echo. It could even be an instrumental residual that survives subtraction, because faint sources live at the edge of calibration. The same pixels can hold several stories. The difference between those options is not philosophical, it is measurable. A planet should be stable in position and repeatable in brightness within orbital expectations, even if weather adds some variability. Dust should show a broader spectrum and perhaps extended structure, and it may evolve on timescales tied to grain dynamics. A flare afterglow should fade and correlate with contemporaneous variability, and it may show a characteristic cooling curve. Instrumental artifacts should correlate with observing setup and reduction choices, not with astrophysical timing. Proxima's violent personality therefore becomes part of the data model. We cannot interpret Webb without modelling the star's time variability, because the star is a variable source in the same bands we care about. We cannot interpret possible planets without modelling how activity contaminates detection methods, because the star can imitate orbital signals. We cannot interpret habitability without modelling atmospheric survival under repeated high-energy bursts, because average energy is not the whole environment. Around Proxima, the extremes may matter as much as the mean. This chapter ends by tightening the suspense rather than resolving it. Proxima is the nearest red dwarf, and red dwarfs are the galaxy's default stars, so what we learn here scales outward. If we can read Proxima correctly, we learn how to read most planetary systems, including those too distant for detailed study. If we misread it, we miscalibrate the odds of life everywhere, because we will be wrong about the most common stars. The stakes are statistical as well as personal. The central question returns with sharper edges. What exactly is strange in JWST's infrared view of Alpha Centauri, and how much of that strangeness belongs to Proxima's flares, dust, or planets? The nearest system should be the easiest to interpret because proximity usually means clarity. Proxima makes it the hardest in the most instructive way, because closeness reveals complexity. The more we can see, the more we must explain. Next, we follow the evidence into Proxima's candidate worlds and Webb's constraints. We ask what signals survive when the star's violence is treated as physics, not background noise. We prepare to separate an orbiting source from a star that never stops changing, and we prepare to accept whatever answer the patterns demand. We have a strange infrared hint, but hints need a census to become evidence, and evidence needs context to become a story. Before we chase the anomaly, we inventory the planets we know, the planets we suspect, and the planets our methods still miss. In practice, that inventory is not a tidy list. It is a map of sensitivities, biases, and hard-won lessons about how stars misbehave. Alpha Centauri should be the easiest nearby system to map because it is close, and because its stars are bright enough to flood our instruments with photons. It is also maddening, because brightness, binarity, and activity pile signals on top of each other until the cleanest patterns blur. The system is like a crime scene under a spotlight. Everything is visible, and yet nothing is simple. The system splits into two search problems that barely talk to each other, even though they share the same neighbourhood. There is the bright binary, Alpha Centauri A and B, where glare and blended light dominate every measurement. There is Proxima Centauri, faint but violent, where activity noise competes with every planetary signature. One side overwhelms detectors, the other overwhelms models, and both punish overconfidence. A planet census starts with definitions, because exoplanet claims are not all the same kind of claim. Some are confirmed with repeated signals, consistent models, and independent instruments that agree on the same period and phase. Others are candidates that survive some tests but fail others, or sit at the edge of detectability where statistics become fragile. In a system this close, the temptation is to treat every bump as a world. Yet the discipline is to ask what would make that bump inevitable. We begin with the confirmed headline Proxima B, because it anchors the entire Alpha Centauri narrative with a real orbit and a real clock. It was detected through radial velocity as a periodic wobble in Proxima's spectrum, a subtle back-and-forth shift in thousands of absorption lines. The period is about 11 days, which puts the orbit in or near the habitable zone depending on climate assumptions and on how harsh Proxima's radiation environment is. In the mind's eye, it is a tight loop close to a dim red star, an orbit you could sketch inside the radius of Mercury's path around our Sun. Radial velocity does not give a true mass, it gives a minimum mass, and that distinction matters for every inference we make. The method measures motion along our line of sight, so the unknown orbital tilt hides the full value behind geometry. Proxima B is Earth-ish in minimum mass, but it could be heavier if the orbit is inclined, sliding it toward a super-Earth regime. That uncertainty is not academic. It changes surface gravity, atmospheric retention, and the likelihood of a thick, volatile envelope. The orbit is compact, which is typical around red dwarfs and not an accident of our imagination. Small stars have close-in habitable zones because they emit less light, so the temperate band sits near the star where orbital periods are short. Their planets also often form or migrate inward, because dense inner disks and migration torques can move material efficiently. The result is a system architecture where multiple short-period planets are common, tightly packed, and dynamically interactive, like beads on a string, each tugging faintly on the others. That architecture matters for habitability, because compact systems remember their early histories in ways wider systems can forget. Migration can move volatile-rich bodies inward, delivering water and carbon compounds, or it can drive resonant chains that later break violently. Close packing can increase early bombardment, and bombardment can both deliver water and strip atmospheres depending on impact speeds and timing. When we ask whether Proxima B could be temperate, we're also asking what kind of childhood it survived. Proxima B is not alone in the data, and the next key entry is Proxima D, a quieter discovery with loud implications. Proxima D is smaller and closer in, detected as a subtle radial velocity signal with a very short orbital period. It sits far inside any habitable zone, where stellar heating would be intense, and the surface, if it has one, would be baked. Yet it proves the system can host multiple small planets, and it strengthens the case that Proxima's inner disk once had enough material to assemble several rocky bodies. Proxima D also proves something about our limits, because its signal is tiny and easy to drown in stellar noise. Detecting it requires disentangling stellar activity from genuine Doppler motion, often by modelling how magnetic regions distort spectral lines. When we can pull out a signal that small, we also learn how easily the star can manufacture false ones. Every successful detection is also a warning label. This is what it took, and this is what could still go wrong. This is the first tension point in the census, and it shapes the mood of everything that follows. If Proxima can host at least 2 small planets, it may host more, because compact multi-planet systems are common around M dwarfs. If Proxima is active enough to mimic planets, some of the remaining signals may be mirages, especially when periods overlap with stellar rotation or magnetic cycles. The census becomes a balance between optimism and skepticism, with the data pulling both ways. The census therefore becomes an investigation into method, not just a list of worlds with names and periods. We need to explain how planets are found, and why Alpha Centauri is both ideal and cruel as a target. The same proximity that boosts signal also exposes every systematic error, because small imperfections no longer average out. When the star is close, even our own instruments become part of the astrophysics. Radial velocity is the workhorse for nearby stars, and the concept is simple enough to say in one breath. A planet and star orbit a shared centre of mass, so the star moves slightly in response to the planet's gravity. That motion shifts spectral lines through the Doppler effect, creating a repeating pattern we can fit with a sinusoid or a more complex orbital model. The visual is elegant, a forest of spectral lines sliding back and forth like a barcode on a conveyor belt. The difficulty is that stars have surfaces, not perfect clocks, and surfaces come with weather. Spots, plages, and convection distort line shapes and shift apparent velocities, producing signals that can look planetary if you're careless. In Proxima, flares and magnetic regions can add quasi-periodic signals that overlap with planetary periods, and the overlap can be cruelly precise. A flare does not just brighten the star, it can change the line profiles we use as our velocity ruler. Stellar rotation is a particular trap because it can create repeating patterns that masquerade as orbital periods. As a spotted star rotates, dark regions move across the visible disk, changing the balance of light from the approaching and receding limbs. That imbalance shifts the measured line centroids, producing an apparent velocity wobble that repeats with the rotation period and its harmonics. If a planet's period sits nearby, the two signals can interfere, like two rhythms that almost match, but never quite lock. For Alpha Centauri A and B, radial velocity faces a different enemy, and it is an enemy made of light itself. The stars are bright enough to saturate detectors and scatter light through optics, creating halos and ghosts that are hard to model. Their spectra can contaminate each other when they are close on the sky, and that contamination changes with time as the binary separation shifts. Even a small leak of one star into the other's spectrum can introduce spurious periodicities, because the two stars have different velocities and different line patterns. Transit detection is the cleanest method when it works, because it measures a planet's size in a direct geometric way. A transit is a small dip in brightness when a planet crosses the stellar disk, and the depth tells you the planet-to-star area ratio. The period gives an orbital clock, and repeated transits lock the geometry with almost obsessive precision. Visually, it is a tiny silhouette drifting across a glowing disk, a cosmic eclipse measured in parts per 10,000. But transits are rare because alignment must be precise, and the universe does not arrange itself for our convenience. A non-detection does not mean there is no planet. It often means the orbit does not cross our line of sight. In Alpha Centauri, transits would be transformative, because a nearby transiting planet becomes a laboratory for atmospheric spectroscopy. Yet we cannot count on them, and we must treat the absence of dips as information with sharp limits. Astrometry attacks the problem from a different angle, measuring position rather than velocity, and it is as old as astronomy itself in spirit. A planet makes its star trace a tiny ellipse on the sky, a wobble superimposed on the star's proper motion and parallax. Nearby stars are prime targets because the angular wobble grows as distance shrinks, turning the same physical motion into a larger apparent shift. The visual is subtle, a point of light that refuses to travel in a perfectly straight line. Astrometry is also brutally demanding because the wobble is tiny even for nearby systems, often measured in microarc seconds. It requires long baselines, stable calibration, and careful modelling of every competing motion, including the Earth's orbit and instrumental drift. In Alpha Centauri A and B, the binary orbit is a large signal that must be removed perfectly because it can dwarf the planetary signature by orders of magnitude. If the binary model is off by a hair, the residuals can impersonate a planet. Direct imaging is the method that matches the public imagination, but it is the hardest in practice, especially for Earth-like worlds. It tries to separate a faint planet from overwhelming starlight, using coronagraphs, wavefront control, and aggressive subtraction algorithms. The challenge is contrast, diffraction, and subtraction, especially with two bright stars creating complex patterns. In the frame, the star is a blinding bloom with rings and spikes, and the planet is a whisper hiding in the glare. In the Alpha Centauri system, direct imaging is both tempting and punishing, because the geometry teases us with the possibility of separation. The stars are close enough that an Earth-like orbit would be a resolvable separation in principle, measured in arc-seconds rather than fractions of one. The glare is so extreme that the planet is still buried, unless the planet is warm, large, or unusually bright in the infrared. Even then, the subtraction must be nearly perfect, and perfection is not a default state of optics. These methods do not compete. They cross-check each other, and the cross-checks are where confidence is built. A radial velocity signal can predict a transit window, even if the probability is low, and it can tell you when to stare. Astrometry can break the inclination degeneracy and turn minimum mass into true mass, changing a maybe Earth-like into a definitely heavier. Imaging can test for luminous companions and map dust that might hide smaller worlds, revealing the environment the planets inhabit. The census is also shaped by a simple fact that is easy to forget. Every method has a preferred kind of planet. Radial velocity loves massive planets on short periods because they tug harder and repeat more often. Transits love large planets around small stars because the dip is deeper and easier to measure. Imaging loves young or warm planets because they glow more brightly in infrared, while astrometry favours massive planets at wider separations that produce larger positional wobbles. When we look at Alpha Centauri, we're not seeing the system as it is. We're seeing the system through these filters. Now we pivot back to the bright binary, because the census there is mostly absence. For decades, observers have searched Alpha Centauri A and B for planets, and the system has served as a proving ground for precision techniques. The record is a sequence of improving limits, punctuated by contested claims that later weakened under reanalysis. Each generation of instruments sharpened the knife, and each time the system slipped away, leaving only tighter constraints. The reason is not lack of effort, it is the difficulty of precision in a bright blended binary, where the target itself changes configuration. Meter per second radial velocity. Precision is achievable, but stellar activity and contamination can produce signals at the same scale. The binary's long-period motion adds trends that must be modelled without leaving residuals, and those residuals can masquerade as planets. Even the act of keeping the instrument stable becomes part of the experiment, because tiny temperature shifts can move spectral lines on the detector. Historically, Alpha Centauri has been a magnet for ambitious claims, because the payoff is so large and the system is so familiar. In the early era of exoplanet hunting, nearby sun-like stars were the dream targets, and Alpha Centauri A looked like the closest analogue to our own sun. As techniques improved, the community learned a hard lesson. Proximity does not guarantee simplicity, and brightness can be a curse. The binary nature adds a moving background that no single star pipeline can ignore. Current limits increasingly rule out certain kinds of planets in certain orbits, and those limits are meaningful even when they are negative. Close-in super-Earths and Neptunes around A or B would likely have been seen by now in many configurations, because their tugs would be strong and frequent. Farther out, gas giants become harder, because periods are long and signals require decades of coverage. When the orbit takes years, the data must span years, and the patience must match the physics. The census therefore has a shape that is itself a clue, like an outline left by what we cannot yet see. Around A and B we have strong constraints in short periods and weaker constraints at longer periods, because time is the limiting reagent. Around Proxima, we have confirmed small planets close in, plus a noisy environment that can hide additional bodies. The system is asymmetric in our knowledge, and that asymmetry guides where surprises can still live. This is where the chapter's investigative core locks in, because the infrared hint from JWST could be a breadcrumb toward missing planets. Missing planets could be in stable zones around A or B, where our radial velocity limits are strong but not absolute. They could be in Proxima's outer system, where periods lengthen and signals thin out into the noise. They could also be embedded in dust structures that complicate every measurement, turning the environment into camouflage. To understand that breadcrumb, we need the stability map in plain terms, because not every orbit is allowed in a binary. In a binary, circumstellar planets must orbit close to their host star to remain stable, staying deep inside the star's gravitational domain. Circumbinary planets must orbit far enough out that the binary acts like a single gravitational source, smoothing the perturbations into one averaged pull. Between those regimes is a chaotic zone where orbits can be pumped eccentric, destabilized, and eventually ejected. Alpha Centauri A and B have habitable zones that sit at different distances because their luminosities differ, and that difference matters for the overlap with stability. A's temperate band lies farther out than B's because A is more luminous and warms planets at greater distances. Stability constraints pull allowable circumstellar orbits inward, especially when the companion star approaches at certain points in the binary orbit. The overlap between habitability and long-term stability is narrow and time-dependent, and it changes subtly as the binary separation varies. That narrowness does not forbid planets, it sharpens the question into something almost philosophical. If a planet exists in A's or B's habitable zone, it must survive repeated perturbations over billions of years, enduring a companion star that periodically tugs at its orbit. If it does not exist, the absence may reflect formation difficulty as much as detection limits, because planet building in a perturbed disk is not the same as planet building around an isolated star. The system forces us to ask whether habitable zone is a place, or a process that must remain stable. The binary also complicates the early disk environment, which is where planets are born and where architectures are set. A companion star can truncate a protoplanetary disk, limiting the reservoir of solids and gas at wider radii. It can also stir the disk, increasing collision speeds between planetesimals and making growth harder in certain regions. Yet disks can also adapt, forming dense inner zones where growth is efficient and leaving behind belts of debris that persist. The outcome is not predetermined, but it is constrained by dynamics. Red dwarfs tell a different architectural story, and Proxima is the example we can test with real detections. Multiple close-in planets are common around M dwarfs in the broader exoplanet census, and surveys have shown that small planets are abundant there. That pattern suggests efficient formation of compact systems plus migration or in situ assembly and dense inner disks where solids drift inward. In simple terms, the building blocks may pile up close to the star and the planets assemble where we now find them. Compact systems also imply strong early interactions with the disk and with each other, and those interactions can leave scars. Resonances can capture planets into chains, locking their periods into simple ratios, then break as the disk dissipates and damping weakens. The aftermath can leave planets on slightly eccentric orbits, increasing tidal heating and altering climate histories. A tiny eccentricity, sustained over time, can mean a lot of internal energy, and internal energy can mean volcanism or tectonic recycling. For Proxima B, the compact orbit means tides are not optional, they are part of the climate equation. Tidal forces can circularize orbits and influence rotation states, shaping day-night patterns and atmospheric circulation. If the planet becomes tidally locked, one hemisphere faces the star and the other faces darkness, and the atmosphere must transport heat to avoid collapse. Tides can also drive internal heating, which can help maintain geology that replenishes an atmosphere even as stellar wind tries to erode it. The star's activity adds another layer that cannot be ignored because Proxima is magnetically restless. Flares and high-energy radiation can strip atmospheres, especially early in the star's life when activity is stronger and more frequent. Yet atmospheres can also be replenished by volcanism, impacts, and outgassing, depending on the planet's interior and volatile inventory. The question is not only whether Proxima B sits in the habitable zone, but whether it can keep an atmosphere long enough for habitability to matter. For Proxima D, the proximity makes tides even stronger, and the environment harsher in ways that are almost guaranteed. It is a reminder that many systems contain inner scorched worlds that are easy to detect, because they tug more strongly and repeat more often. Those worlds can also be signposts of migration pathways, hinting that material moved inward and that other planets may have formed farther out. In a compact system, the innermost planet is rarely the whole story. It is the part we can see first. The census also forces us to confront what missing means in a quantitative sense. Missing can mean below our detection threshold, where the signal is smaller than the noise floor of the instrument and the star. Missing can mean hidden by geometry, as with transits that never align. Missing can mean confused with stellar variability, where the star generates a pattern that looks planetary until you model it better. In Alpha Centauri, missing is not a single category, it is a spectrum of invisibility. Now, we bring JWST into the census, but with a careful correction, because expectations can outrun the physics. JWST is not primarily a planet finder for bright nearby stars, especially not for Earth analogues in reflected light. JWST is a tool for thermal emission, dust characterization, and spectroscopy when geometry and contrast allow. It is a machine for faint infrared structure, and that structure can be planetary, dusty, or instrumental. In the infrared, JWST can measure excess emission above the stellar photosphere, and excess is the key word. That excess can come from warm dust, from a luminous companion, or from a combination that changes with wavelength. JWST can also measure spectral slopes that hint at temperature, grain properties, and composition, because different materials emit differently across infrared bands. In a clean case, the spectrum becomes a thermometer, and the colour becomes a clue. For planets, JWST's strength is often follow-up rather than discovery, and the distinction matters for how we interpret a hint. If a planet transits, JWST can probe atmospheric molecules through transmission spectra, measuring how starlight filters through the limb of an atmosphere. If a planet is warm enough and separated enough, JWST can constrain thermal emission or phase variations, though bright star systematics remain severe. Even then, the analysis is a battle against residual starlight and against the instrument's own subtle changes. For dust, JWST is unusually powerful because dust is an infrared object by nature, and it announces itself through heat. Dust grains absorb starlight and re-radiate it, producing a glow that can exceed a planet's thermal signal at the same separation. In an old system, warm dust is especially interesting because it should not persist without replenishment, since grains collide, fragment, and spiral inward under radiation forces. If we see warm dust today, something is feeding it, and that something is often dynamical. This is where missing planets and dust become entangled, because planets do not just sit in dust, they sculpt it over time. Gravity can shepherd grains into rings, clear gaps, and trap material in resonant clumps that orbit in step with the planet. The sculpting is slow but relentless, and it can turn an initially smooth disk into a structured pattern. In the visuals, a faint ring becomes a sharper band, and a gap opens like a lane cut through fog. A single unseen planet can create a pattern that looks like a symmetry in infrared brightness, and a symmetry is exactly the kind of thing that catches attention. A planet can concentrate dust at preferred longitudes, producing a lopsided ring that is brighter on one side. It can also open a gap whose edges glow brighter, creating a false impression of multiple components. What looks like two features can be one structure shaped by a single perturber. In a binary, the sculpting has extra layers because the stars already impose resonances and forced eccentricities on surrounding material. The binary can clear regions and create stable islands where dust survives longer, even as other zones are swept clean. That means a dust asymmetry could be planetary, binary-driven, or both, and the patterns can overlap in confusing ways. The system becomes a superposition of sculptors, each leaving a signature that can mimic the others. We can translate these ideas into testable predictions, and predictions are how a mystery becomes an experiment. A planet-driven clump should move with orbital phase, maintaining a consistent relationship to the star over time. A transient dust cloud from a collision should fade and spread, changing brightness and morphology across months to years. The sky itself becomes the timeline, and repeat observations become the interrogations. A warm debris disk or zodiacal cloud should produce a smoother, more extended excess, and its structure should not collapse into a single point at JWST's resolution. Its spectrum should match a range of grain temperatures and sizes, not a single blackbody, because real dust is a mixture. If the disk is dense enough, it can become the dominant noise source for direct imaging of Earth-like planets, effectively raising the background glow. In that case, the obstacle is not the planet's faintness alone, it is the system's own dust shining in the same bands. A planet's thermal emission should behave more like a point source at JWST resolution, especially if it is compact and not embedded in a bright disk. Its spectrum should be consistent with a warm body, potentially modified by an atmosphere that redistributes heat. If the source is real and bound, it should share proper motion with the star system, shifting across the background of distant stars in the same direction. Proper motion becomes a fingerprint, separating local companions from distant coincidences. The census therefore turns into a forensic exercise, where we treat every clue as conditional. We ask which explanation fits the brightness, the colour, the spatial distribution, and the repeatability across observing epochs. We also ask which explanation survives the instrument test that bright targets demand, because Alpha Centauri is a stress test for data reduction. In this environment, the line between feature and artifact is thin, and the only way to thicken it is repetition. Instrument systematics are not a footnote in Alpha Centauri. They are part of the story and part of the suspense. Point spread functions have rings and spikes that shift with wavelength and pointing, and those patterns can leave residuals after subtraction. Subtraction residuals can create false clumps that look astrophysical, especially near saturation and scattered light. A bright star can imprint a ghost structure that seems to sit in space, until you rotate the telescope and watch the ghost rotate too. Time variability adds another layer, especially around Proxima, where flares are frequent and sometimes dramatic. Flares can change the star's infrared output and heat nearby dust transiently, creating a temporary glow that fades as grains cool. If the strange signal appears in only one epoch, we must ask whether it is a flare echo rather than a stable structure. The question becomes uncomfortable. Are we seeing a companion, or a momentary afterimage of stellar violence? Even the binary stars themselves can complicate the infrared scene, because their combined light creates a changing illumination pattern. As A and B move in their orbit, the geometry of scattered light and diffraction changes, and subtraction templates can become imperfect. A small mismatch in the model can leave a residual that looks like a faint source, especially near the region where a planet would be most interesting. In a system like this, the data reduction pipeline is not just processing. It is a hypothesis about what the instrument should have seen. This is why the chapter's mood stays mysterious, but the logic stays strict, because the system rewards discipline. Alpha Centauri is close enough to tempt certainty, yet complex enough to punish it with false positives and near misses. The strange JWST hint is not a conclusion, it is a constraint that forces us to narrow the field. In science, a constraint is a kind of progress, even when it feels like a delay. We now set the narrative hinge for the rest of the investigation, and we do it with clear alternatives. There are 3 competing explanations for the strange JWST signal, and each one demands a different next observation. The documentary becomes a scientific whodunit, where the culprit must match the physics, the statistics, and the behaviour over time. The suspect list is short, but the alibis are technical. Explanation 1 is an unseen planet, likely shaping dust or contributing its own thermal glow, and it is the most tempting because it feels like discovery. This could be a missing world around Proxima, perhaps farther out where radial velocity sensitivity drops and periods stretch. It could be a stable zone planet around A or B that has evaded radial velocity because of inclination, activity, or contamination. If true, the signal should repeat and move predictably with orbital dynamics, returning like a scheduled appointment. A planet explanation also implies a broader architecture, because planets rarely form alone in isolation. If one planet is shaping dust, there may be additional bodies that maintain the disk's structure, or stir collisions that replenish grains. The infrared hint could be the visible edge of a larger dynamical system, one that our current census only partially captures. The thought is unsettling and exciting. What if the system is rich, and we're simply looking with the wrong filters? Explanation 2 is warm dust, a debris disk or zodiacal cloud that is brighter or more structured than expected, and it is plausible because dust is a natural infrared emitter. If true, the spectrum should favour grain emission, and the structure should align with plausible belts and resonances. The brightness would imply active replenishment through collisions or comet delivery, because old dust should fade without a source. That replenishment in turn would hint at ongoing dynamical stirring, which is often driven by planets. Dust also raises a subtle observational challenge, because it can imitate a planet while being physically very different. A concentrated clump of grains can look point-like at a given resolution, especially if it sits near the instrument's detection limit. Yet dust should behave differently with wavelength, because grain size distributions change the colour and the scattering properties. The question becomes, does the feature keep the same identity across bands, or does it dissolve into a spectrum of dust temperatures? Explanation 3 is time-variable stellar activity, or observational systematics, and it is the most deflating but often the most honest. If true, the feature should correlate with flare timing, calibration choices, or instrument orientation, and it should not behave like a bound object. It should fail the test that real sky features pass, like rotating with the sky across roll angles rather than with the telescope's optics. In other words, it should reveal itself as a trick of light, not a new world. The planet census ends with a sharpened question rather than a solved mystery, because that is what a good census does. We have confirmed worlds at Proxima, and we have decades of constraints at A and B, and those facts narrow the plausible space. We also have a JWST breadcrumb that could point to a missing planet, or to dust, or to a calibration trap waiting for the unwary. The system remains close, bright, and stubbornly ambiguous. Next, we follow the evidence into the strange infrared signal itself, treating it like a suspect under interrogation. We compare methods, epochs, and models until one explanation predicts the data better than the others, and we do it without granting any method automatic trust. In Alpha Centauri, the only path to discovery is discipline repetition, because repetition is how you tell a real orbit from a coincidence. The census has done its job. It has told us what we know, what we do not, and exactly where the mystery can still hide. Four light-years away, Alpha Centauri should feel readable, almost familiar, and yet Webb's infrared returns patterns that resist a simple story. In visible light, the system is a bright, steady beacon, but in infrared it becomes layered, glow over glow, where the meaning depends on how we untangle it. This chapter slows down and shows how astronomy turns photons into evidence, and how strange is defined inside real data. It is not a ghost story about a surprising dot, It is a procedural story about how surprises survive contact with skepticism. We begin with Webb itself, because every conclusion inherits the telescope's design, its strengths, and its blind spots. JWST is a segmented mirror acting as one large collector, built to gather faint infrared light efficiently across a wide field. Each hexagonal segment is aligned with exquisite precision, so the combined surface behaves like a single optical figure. That alignment is not just engineering pride, it shapes the sharpness of every star and the shape of every halo. When we talk about a faint excess near Alpha Centauri, we are also talking about how that segmented mirror distributes light. Webb operates in deep cold, so the observatory's own heat does not masquerade as a signal, and that cold is not optional. Infrared detectors see warmth the way night vision sees body heat, so a warm telescope would be a flashlight pointed at itself. The sunshield blocks sunlight, earthlight, and moonlight, and it creates a permanent shadow where the optics can settle. Sensitivity is the headline, but stability and calibration are the quiet requirements that make sensitivity useful. A telescope that is sensitive but drifting is like a microphone that amplifies everything, including its own hum. There is also a historical echo here, because infrared astronomy has always been a fight against self-generated heat. Early infrared detectors on the ground were limited by the atmosphere's own glow and by the telescope structure warming and cooling through the night. Space missions like IRIS and Spitzer pushed past those barriers, and they taught astronomers to treat thermal backgrounds as data that must be modelled. Webb inherits that lineage, but it pushes the precision further because the questions are sharper. We're no longer asking whether dust exists. We are asking whether a subtle pattern is dust, a planet, or an illusion. JWST excels at infrared because infrared is where warm dust glows and cool planets radiate, even when they are invisible in reflected light. Visible light favours reflected starlight, which punishes us with contrast near bright stars. A small planet beside a bright star is like a firefly next to a searchlight, and the glare dominates the frame. Infrared shifts the contest toward thermal emission, where temperature becomes a measurable signature. That shift is why Webb is central to the Alpha Centauri mystery, and why its returns feel different from older images. In infrared, temperature becomes a kind of language, but it is a language with dialects. A dust grain warmed by starlight emits broadly, while a planet emits with a spectrum shaped by its atmosphere and surface. The same brightness can mean different things if the spectrum bends in different ways across wavelength. Even the word warm is relative, because a few hundred Kelvin is warm for dust and cold for stars. The key is that infrared lets us measure energy that is being re-radiated, not merely reflected. Yet Alpha Centauri is also a worse case for brightness, and brightness creates its own kind of darkness. Bright stars can saturate detectors, pushing pixels into nonlinearity and leaving persistence that lingers after the exposure ends. In practice, that means a star can leave a memory in the detector, a faint afterimage that contaminates later frames. Scattered light and diffraction structure create halos that must be modelled, not wished away. The very optics that give Webb its sharpness also produce predictable patterns, and those patterns can masquerade as faint companions. The challenge is not merely that the stars are bright, but that they are bright in multiple ways at once. Their cores can saturate while their wings still carry useful information, and the transition between those regimes is where calibration becomes delicate. A small error in the detector's response curve can create a false excess that looks astrophysical. A small pointing drift can shift the subtraction residuals into a shape that looks like a clump. In a system as nearby as Alpha Centauri, the data are rich, but the pitfalls are equally rich. So we define the first rule of strange in Webb data, and it is stricter than it sounds. Strange is never just an unexpected bright spot, because optics can manufacture bright spots. Strange is a pattern that survives instrument checks, reduction choices, and repeated observations. Strange is what remains when the easy explanations are removed, and when the hard explanations have been tested. It is a category defined by endurance, not by drama. That definition matters because astronomical images are not photographs in the ordinary sense. They are reconstructions from detector counts, corrected for bias, dark current, flat field response, and cosmic ray hits. Each correction is necessary, but each correction is also a choice, and choices can move the boundary between signal and artifact. When a team calls something strange, They are saying it persists across those choices. They are saying it is not a single pipeline's personality. Now we introduce Webb's infrared eye in conceptual terms, without drowning in engineering. Near-infrared covers hotter emission and reflected components, and it is sensitive to certain molecular bands that can hint at composition. Mid-infrared reaches cooler temperatures, where dust belts and temperate planets emit strongly, and where silicate features can stand out. The same target can look different across these regimes, because temperature and composition change the spectrum. A feature that is bright in one band and absent in another is not a contradiction. It is a clue. Near-infrared is where you still feel the influence of starlight, because the star's spectrum remains strong there. Mid-infrared is where the star fades and the environment can speak more clearly, though the background becomes more complex. Thermal emission from dust peaks in the mid-infrared for many inner system temperatures, and that is why these wavelengths are so diagnostic. But mid-infrared also demands careful background subtraction, because the telescope and the sky contribute their own low-level glow. Webb's design minimizes that glow, yet it never disappears entirely. Imaging tells us where light is on the sky, and how extended or compact it appears when blurred by the telescope's resolution. Spectroscopy tells us how that light is distributed across wavelength, which is where fingerprints live. Imaging can reveal asymmetry and offsets, but it can confuse point sources with compact dust clumps. Spectroscopy can separate dust-like slopes from planet-like curves, but only if the starlight is controlled. Together they form a cross-examination, where each method challenges the other's assumptions. A useful way to picture this is to imagine two maps of the same landscape. Imaging is the aerial view, showing where the bright patches sit relative to the star. Spectroscopy is the soil analysis, telling you what the bright patches are made of. In practice, Webb often combines these approaches, using filters that sample specific wavelength regions and using spectral modes that spread light into detailed distributions. The more detailed the distribution, the more sensitive it becomes to calibration and to residual starlight. The central technical challenge is separation, because the stars dominate every frame even when we try to look away from them. Astronomers use point spread function modeling to predict how a star's light should spread across the detector. They subtract that model to search for leftover emission that could be dust or a companion. They also use roll angles and multiple visits, because real sky features stay fixed on the sky, while optical artifacts rotate with the telescope. That simple geometric trick becomes a powerful test of reality. The point spread function is not just a blur, it is a structured pattern shaped by diffraction, by mirror segmentation, and by small optical imperfections that are stable but not trivial. In Webb images, diffraction spikes and rings can be crisp, and their intensity can vary with wavelength. If subtraction is slightly misscaled, those rings can leave arcs that look like partial disks. If the centering is slightly off, a residual can appear as a false offset. The PSF is predictable, but it is not forgiving. This is where the chapter's tension rises, because subtraction is both powerful and dangerous. An imperfect PSF model can leave structured residuals that mimic rings, clumps, or point sources. Over-subtraction can carve out negative bowls that hide real emission, making a real disk look like a gap. Under-subtraction can inflate a faint excess into something that looks dramatic, especially when contrast is stretched for visibility. The same data can look calm or alarming depending on how subtraction behaves. So we ask what infrared evidence actually looks like when it is behaving, and that question has a disciplined answer. A star's photosphere has a predictable spectrum that can be modelled from temperature and radius, and its infrared tail is especially well behaved. If the measured flux rises above that photosphere at longer wavelengths, we call it an infrared excess. Excess is the first hint of dust or a cool companion, but it is not yet a diagnosis. It is a flag that says, something else is radiating here. The logic is deceptively simple, but the practice is careful. You model the star, then you measure the star, then you compare them with uncertainties that include instrument calibration. If the difference is larger than the error bars, you have an excess. But the error bars must include subtle systematics, like detector response drift and background subtraction. In bright star regimes, even small systematics can dominate the uncertainty budget. That is why excess is a threshold concept, not a poetic description. Thermal emission follows a curve that depends on temperature, and temperature implies location for material heated mainly by starlight. Dust grains closer to a star are warmer and peak at shorter infrared wavelengths. Grains farther out are cooler and peak deeper into the mid-infrared, and eventually into far infrared regimes beyond Webb's reach. If we infer a dust temperature, we can estimate a characteristic distance, but only after accounting for grain physics. Otherwise, the distance estimate can be wrong by a factor that matters. The underlying physics is energy balance, which sounds abstract but is intuitive in plain language. A grain absorbs starlight and emits infrared until it reaches a steady temperature. If it absorbs efficiently and emits efficiently, it behaves like a blackbody and the temperature maps cleanly to distance. If it absorbs or emits inefficiently at certain wavelengths, the temperature shifts. That inefficiency depends strongly on grain size relative to the wavelength of light. In other words, a grain's microscopic scale can change the macroscopic map we draw of the system. Real dust is not a perfect blackbody, and that is where composition matters and where infrared becomes a diagnostic tool. Small grains emit inefficiently at long wavelengths, which makes them appear warmer than their distance would suggest. Silicate grains can show features that stand out in mid-infrared spectra, especially around characteristic bands, and those features are tied to vibrational modes in the mineral lattice. Carbonaceous grains and ices shift the spectral shape in different ways, changing both slope and features. Composition is chemistry made visible through heat. Even within silicates, the story can vary, because crystalline and amorphous structures imprint different spectral textures. A smoother feature can suggest more amorphous material, while sharper substructure can indicate crystallinity, which often implies thermal processing. Ices can add their own signatures, but they also sublimate if they are too close to the star, so their presence hints at colder zones. Carbon-rich grains can darken the spectrum and alter how efficiently grains absorb starlight. Each ingredient changes the balance between absorption and emission. We translate this into the simplest possible inference chain, and we keep it honest. Measure excess, fit a temperature-like curve, check whether the curve matches plausible grains and plausible distances in the Alpha Centauri environment, then test whether the same interpretation holds across filters, epochs, and independent instruments. The chain is simple, but the tests are strict because each link can break. At this point, it helps to remember what environment means in a binary system. Alpha Centauri A and B orbit each other, and their changing separation changes the gravitational landscape for dust and planets. Stable zones exist, but they are shaped by the binary's long-term dynamics. A dust belt around one star can be perturbed by the other, and a circumbinary structure would face different constraints. When we infer a dust distance from temperature, we also ask whether that distance is dynamically plausible. Now we define the anomaly space, because strange can mean several different things in Webb observations, and each kind of strange points to a different kind of physics. One kind of strange is excess emission, where models predict little, especially in an old system where warm dust should fade. Another kind of strange is an unexpected spectral slope that does not match typical debris disk grains. A third kind of strange is spatially offset brightness, where the emission is not centered where starlight subtraction says it should be. A fourth kind of strange is time variability that does not fit a stable disk. Each of these anomalies points to different physics, and the chapter treats them as competing hypotheses rather than as a single mystery box. Excess emission can be dust, a planet, or a calibration error. A slope mismatch can be unusual composition, unusual grain sizes, or a mixed source. An offset can be a companion, a dust clump, or a PSF residual. Variability can be collisions, stellar activity heating dust, or instrumental drift. The same image can host multiple stories, and the job is to see which story survives. We anchor the discussion in Alpha Centauri's specific constraints, because context prunes the hypothesis tree and prevents us from fantasizing. Alpha Centauri A and B are bright enough to stress Webb's detectors and create complex scattered light patterns. The binary geometry changes over time, which changes contamination and subtraction difficulty as the stars move relative to the instrument's field. Proxima is fainter but active, and activity can create time-dependent infrared backgrounds. Even the system's proximity becomes a constraint, because it makes motion tests unusually powerful. Brightness is not only a detector problem, it is an optical problem that shows up as structured glare. Diffraction spikes can cut across the field, and their orientation depends on the telescope's role. Scattered light can create gradients that are subtle but persistent, and those gradients can bias background estimates. In a faint target field, you might ignore a small gradient. In Alpha Centauri, a small gradient can be the difference between disk and artifact. That is why teams treat bright star observations as their own specialized discipline. We return to the system's age because it makes warm dust suspicious in a useful way, and suspicion is part of good science. In a multi-giga-year system, small grains should be removed by collisions and drag unless replenished. Radiation pressure can push the tiniest grains outward, while pointing, Robertson drag, can cause others to spiral inward over long timescales. A persistent warm component implies ongoing supply, such as collisions in a belt, comet delivery, or resonant trapping. That replenishment often implies unseen bodies stirring the system, because quiet systems do not grind dust efficiently. This is one of the deeper reasons debris disks matter, even when they are faint. Dust is short-lived compared to the age of a mature star, so seeing dust is often like seeing smoke. The smoke does not tell you exactly what burned, but it tells you something is happening. In young systems, dust is expected because planet formation is messy and violent. In older systems, dust can still exist, but its presence demands a mechanism. That mechanism is often dynamical, and dynamics often means planets. Now we introduce debris disks and exozodiacal light as both evidence and obstacle, because they play both roles at once. Exozodiacal dust is the analogue of our zodiacal cloud, a diffuse glow from grains in the inner system, created by collisions and by the slow grinding of larger bodies. It matters because it traces dynamical activity and collisional evolution. It also matters because it acts like fog for future direct imaging of Earth-like planets. The same dust that teaches us about architecture can hide the very worlds we want to see. In our own solar system, zodiacal light is visible from dark sites as a faint triangular glow before dawn or after dusk. That glow is sunlight scattered by dust, and in infrared it becomes thermal emission that traces the dust temperature distribution. When we talk about exozodi around Alpha Centauri, we are talking about an analogue of a familiar phenomenon, but potentially at a different intensity. A small increase in dust brightness can have outsized consequences for planet detection. It raises the floor against which we must detect a tiny signal. If exozodi is bright, it raises the background and lowers the effective contrast for small worlds. A planet can be present and still be hidden inside dust emission that looks smooth at limited resolution. Dust can also create false positives, because a clump can mimic a point source when blurred by the PSF. In Alpha Centauri, where we crave Earth-like targets, exozodi becomes a strategic constraint. It is not only a scientific curiosity, it is a mission planning parameter. This is where the visuals in our minds should slow down and sharpen. Imagine a dark field with a bright central star, then imagine a faint broad glow around it, like breath on glass. Now imagine trying to pick out a tiny ember inside that breath. That is what exozodiacal dust does to direct imaging, and it does it even when the dust is physically thin. The problem is not thickness, it is brightness relative to the planet. Webb's infrared sensitivity makes it possible to measure that fog, but it also makes the fog impossible to ignore. We now show what a planet should look like in Webb's infrared, at least in principle, because principles guide the tests. A planet's thermal emission is compact and follows a temperature-driven spectrum, often approximated by a modified blackbody. If the planet has an atmosphere, molecular absorption can carve broad features into the spectrum, shaping the curve in recognizable ways. If the planet rotates or has weather, brightness can vary, but it should vary in ways tied to orbit and phase. A planet is not just a dot, it is a dot with rules. Those rules can be subtle, but they are real. A planet's brightness can change as it presents different hemispheres, especially if it has continents, clouds, or hotspots. The spectrum can show muted bands from molecules like water vapor, carbon dioxide, or methane, depending on temperature and composition. In the mid-infrared, those bands can be broad, and they can alter the slope enough to distinguish a planet from simple dust emission, but only if the measurement is clean enough to trust the slope. We contrast that with what dust should look like, again in principle, because dust has its own rules. Dust emission is often extended or at least broader than a true point source, depending on distance and instrument resolution. Its spectrum can be a blend of temperatures, because a belt contains grains at many radii and sizes, and each grain type emits differently. Dust can show compositional features, but those features can be subtle when mixed across grain populations. A belt is an ensemble, and ensembles blur signatures. Dust also has geometry, and geometry matters because it shapes surface brightness. A face on disk can look like a symmetric glow, while an edge on disk can look like a thin band with brightened ansai. A narrow belt can look like a ring, but only if the subtraction is good enough to reveal it. A broad distribution can look like a gentle gradient that is easy to misinterpret as background. Even when dust is real, it can hide in plain sight if we do not model its expected profile. Then we admit the uncomfortable truth that drives the chapter's mystery, and it is a truth about limits. The line between planet and dust can blur, especially near detection limits where the data are sparse and the systematics are loud. A compact dust clump can appear point-like, and a planet embedded in dust can inherit dust-like colours. A mixed signal can fit multiple models, and each model can sound plausible in isolation. The danger is not ignorance, it is overconfidence. So we define the discriminants that matter most in practice, and we treat them like a checklist rather than a hunch. Does the source move like an orbiting companion, or does it stay fixed like a background object? Does it share the system's proper motion across months and years, which is large for a nearby star? Does it persist across roll angles, or does it rotate with the instrument? Does it keep the same spectrum across independent reductions, or does the spectrum change with processing choices? Each discriminant is a way of asking whether the sky or the telescope is speaking. Proper motion is especially powerful here, because Alpha Centauri slides across the background sky noticeably over time. A distant galaxy or background star will not follow that motion, so a candidate that stays aligned with Alpha Centauri is more likely to be associated. But even that test has nuance, because a subtraction residual will also follow the star by definition. That is why proper motion must be paired with roll angle tests and with modelling of the PSF. No single test is sovereign. We also define the discriminants that are easy to misuse, because the chapter is about discipline as much as discovery. A single best fit temperature can be misleading when grains are non-black body and when multiple grain populations coexist. A single apparent offset can be misleading when PSF subtraction leaves structured residuals that pull the centroid. A single epoch can be misleading when variability and persistence exist, especially after saturation. Strange requires convergence across tests, not a single impressive plot. In real data, the most convincing result is often the least cinematic. Now we walk through the specific anomaly types that Webb could plausibly flag in Alpha Centauri, and we keep each one grounded in physical mechanisms already on the table. Warm dust, where models predict little, could mean a recently activated collisional cascade, where larger bodies are being ground down into smaller grains. It could mean comet delivery triggered by long-term dynamics in the binary, sending icy bodies inward to sublimate and shed dust. It could mean resonant trapping that concentrates grains and slows their removal, making the dust look brighter than expected. Each option implies motion and structure we might later detect. A collisional cascade is not a single crash, but a chain reaction over time. One collision produces fragments, fragments collide again, and the size distribution shifts towards smaller grains that radiate efficiently in infrared. The cascade can be sustained if a reservoir of larger bodies keeps feeding it, and that reservoir can be stirred by planets or by binary perturbations. If the cascade is recent, the dust can be temporarily enhanced, and the infrared excess can appear unexpectedly strong. The question becomes whether the enhancement is transient or persistent. Comet delivery is a different flavour of replenishment, and it has its own signatures. Inward scattered bodies can release dust closer to the star, creating a warmer component that peaks at shorter infrared wavelengths. If the delivery is episodic, the dust brightness can vary, and the composition might lean toward volatile, rich materials. In a binary system, long-term gravitational interactions can reshape reservoirs and open pathways that are closed in single-star systems. The dynamics can be slow, but the consequences can be sudden. Asymmetry is a sharper clue, because asymmetry implies a recent event or an ongoing sculptor, and symmetric disks are the default expectation. A lopsided brightness pattern can follow a recent collision that produced a localized cloud, which then shears and spreads under orbital motion. It can also follow a planet's resonant forcing that concentrates dust at preferred longitudes, creating a persistent clump that moves with the planet. In a binary, asymmetry can also be driven by forced eccentricity and time-dependent illumination. The disk is not only material, it is a dynamical response. Visually, asymmetry is where the scene feels alive. Instead of a smooth halo, you see a brightened arc, a knot, or a one-sided enhancement that refuses to average out. But the eye can be fooled because subtraction residuals can also be one-sided if the PSF model is imperfect. That is why asymmetry must be tested across roll angles and across wavelengths. A real asymmetry stays on the sky, while an instrumental one pivots with the telescope. The difference is geometric, and geometry is hard to argue with. A brightness offset is the most tempting kind of strange, because it whispers "companion" in a language we are primed to hear. If emission is consistently displaced from the star's center, in multiple bands and epochs, a bound object becomes plausible, but offsets can also come from imperfect centering, saturation effects, or wavelength-dependent PSF structure that shifts the apparent centroid. The chapter keeps that temptation under control by insisting on repeatability and on independent confirmation. In bright star work, temptation is the enemy of accuracy. Offsets also interact with the binary nature of Alpha Centauri in subtle ways. When two bright stars sit in the same neighborhood, their halos can overlap, and subtraction errors can pull residuals toward or away from the companion star. The geometry changes as the binary orbits, so an offset that appears at one epoch might not appear the same way later. That variability can be astrophysical, but it can also be purely optical. Teams must ask whether the offset tracks the sky or tracks the changing glare pattern. The answer is not found in one image. Time variability is the most dramatic and the most treacherous, because it feels like a smoking gun even when it is not. A stable debris disk should not change rapidly in total brightness, though small variations can occur as viewing geometry and illumination change. A transient dust cloud from a collision can fade and spread over months to years, changing both brightness and shape. Stellar activity can heat dust briefly, and it can also change the star's infrared output in ways that leak into subtraction. Variability can be real, but it can also be a processing echo. Detector persistence adds another layer to this, because it can create apparent variability that is purely instrumental. If a saturated star leaves a residual signal that decays over time, later exposures can show faint structures that were not present earlier. Those structures can mimic a fading dust cloud unless the observation sequence is carefully analysed. That is why observation planning, including exposure timing and dithering patterns, matters for interpretation. In a sense, the schedule becomes part of the dataset. We connect variability to Proxima's behaviour, because Proxima is the system's time-variable engine and a reminder that stars are not always quiet. Flares can change the star's spectrum and create afterglow-like contamination in infrared bands, especially when the system is observed repeatedly. If a feature appears only during or after an active episode, it demands a flare correlation test. If it repeats on an orbital clock, it demands a companion test. The same flicker can mean magnetic activity or orbital mechanics, and the data must decide. Proxima's activity is also a cautionary tale about interpreting infrared light as purely thermal emission from dust. A flare can heat the stellar atmosphere and alter the near-infrared continuum, and even small changes can matter when subtraction is tuned to high precision. Activity can also change the background through scattered light and detector response, creating subtle differences between visits. The system is nearby, but it is not simple. Proximity gives us leverage, yet it also exposes complexity. Now we bring the audience into the logic NASA teams use to avoid overinterpreting a single dataset, because the method is the message here. First, they repeat observations to see whether the feature persists and whether it moves relative to the star. Second, they observe in different filters to test whether the spectrum matches dust or a planet, rather than matching a single curve by chance. Third, they compare to other telescopes and archives to rule out background sources and confirm proper motion. Fourth, they forward model the instrument response to see whether the feature can be manufactured by known systematics. The sequence is designed to make false positives expensive. Repeat observations do more than add confidence, they add dimensions. A second epoch can reveal motion, fading, or stability, and each outcome narrows the hypothesis space. A third epoch can show whether a trend is real or whether it was a one-off artifact. In a nearby system, even small orbital motion might be detectable over months, depending on separation. For dust, repeated observations can show whether a symmetry rotates or smears as expected. Time becomes a diagnostic tool. Filter diversity is equally important because it tests the spectrum without requiring full spectroscopy. If a feature is dust, it might brighten at longer wavelengths in a way consistent with cooler emission, and it might show hints of silicate structure. If it is a planet, it might show a different colour temperature and a smoother continuum shaped by atmospheric absorption. If it is an artifact, it may not behave consistently with wavelength, or it may track known PSF changes. The point is not to chase a perfect fit, but to seek consistency. Archival comparison adds a different kind of leverage, because the sky has a memory. Background galaxies and stars have known positions, and their infrared brightness can sometimes be checked against catalogues. If a candidate feature sits where a background object should be, that is a straightforward explanation. If it moves with Alpha Centauri, the background explanation weakens. This is where the system's large proper motion becomes a gift, because it lets the star sweep past background fields like a moving spotlight. The background stays, the system moves. Forward modelling is not decoration in this story, it is the courtroom where claims are tested under controlled conditions. Teams simulate PSFs, detector behaviour, and subtraction pipelines to predict what artifacts look like when the system is pushed into extreme contrast. They also simulate dust belts with grain physics to predict spectral slopes and spatial profiles that Webb should recover. They simulate planets with atmosphere models to predict broad molecular absorption and phase behaviour across filters. The goal is not to fit the data once, but to see which model predicts new data best. Prediction is the difference between explanation and storytelling. Modelling also forces teams to quantify uncertainty rather than to gesture at it. How sensitive is the result to centering errors of a fraction of a pixel? How sensitive is it to background estimation in the presence of scattered light gradients? How sensitive is it to the assumed grain size distribution in a dust model? Each sensitivity test is a way of asking whether the conclusion is robust or brittle. A robust conclusion survives reasonable perturbations. A brittle one shatters when a parameter shifts. We emphasize that Alpha Centauri forces unusually strict standards because the system sits at the intersection of opportunity and difficulty. Bright star challenges make saturation and scattered light more likely, and they make PSF subtraction more demanding. Binary geometry makes contamination and subtraction more complex because two bright sources can influence the same field. Proximity makes proper motion tests powerful, but it also makes small systematics visible, because the signal we seek is not buried in noise alone. In a nearby system, precision is not optional. There is also a psychological reason standards tighten here, and it is worth naming. Alpha Centauri is close enough that any hint of a planet feels personal, like a neighbour's porch light turning on. That emotional proximity can bias interpretation if it is not checked. Teams counter that bias with process, with blind analyses, and with independent reductions. The discipline is not cynicism. It is respect for how easily we can fool ourselves with beautiful images. Now we return to the chapter's core question, framed as a disciplined choice among outcomes that each carry weight. If Webb's strange signal is a planet, it implies a hidden world and a new architecture close to home, possibly in a region we hope could host stable climates. If it is dust, it implies active replenishment and recent dynamical stirring in an old system that we expected to be quieter. If it is an artifact, it implies our methods still struggle at the edge of contrast, even next door. Each option teaches us something, but only one can be true at a time. The planet option is alluring because it would reshape our local map of habitability prospects. A nearby planet would become a prime target for future instruments, and it would sharpen the urgency of understanding exozodiacal dust as an obstacle. But the dust option is equally profound, because it would reveal a system still evolving dynamically, still grinding and rearranging material. In that case, the strange signal is not a single object, but a process. The artifact option is sobering, yet it is also valuable, because it would improve the methods that will be used everywhere else. We then connect this choice to why exozodiacal dust matters beyond curiosity, because dust is not merely decoration around a star. Dust is a record of collisions and migration, which are the processes that shape terrestrial planet environments over long timescales. Dust also changes the radiation field by absorbing and re-emitting energy, altering local thermal balance in subtle ways. Dust increases impact rates by tracing reservoirs of small bodies, which can erode or replenish atmospheres. The glow is a clue to the system's physical stress. In practical terms, a dusty inner system suggests an active population of small bodies, and small bodies are the delivery system for both harm and help. Impacts can strip atmospheres, especially on smaller planets, and repeated bombardment can reset surface conditions. But impacts can also deliver volatiles and organics, depending on composition and timing. Dust composition hints at what those impactors might be made of, because dust is the fine-grained product of the same reservoirs. When we read dust, we are reading a proxy for the system's inventory. So whatever Webb is seeing, it changes the habitability conversation, and it changes it in more than one direction. A dusty inner system can mean more impacts and more atmospheric stress, even if planets exist in the right temperature zone. It can also mean more delivery of volatiles, depending on timing and composition, which could help sustain oceans and atmospheres. A hidden planet can stabilize or destabilize belts, shaping long-term bombardment and climate forcing. Habitability is not a single dial. It is a balance of competing influences. We make the transition to habitability explicit, because the documentary's stakes depend on it, and because the word can otherwise feel abstract. Habitability is not only about receiving the right average starlight, it is about whether atmospheres survive, whether surfaces are repeatedly sterilized, and whether chemistry can remain stable long enough for biosignatures to accumulate. In Alpha Centauri, dust and dynamics are part of that survival story. The infrared glow is not just a measurement, it is an environmental indicator. A planet in a dusty system might still be habitable, but the pathway could be narrower. If impacts are frequent, life might need refugees, or it might need long quiet intervals to establish complexity. If volatiles are delivered late, they could replenish atmospheres after early loss. If dust is concentrated by resonances, it could signal the presence of planets that shape stable zones. The same dust that complicates detection could be telling us where the architecture is most organized. The obstacle becomes a map. We also underline a subtle point that will matter in later chapters, because it connects observation to interpretation. Biosignatures are interpreted through spectra, and spectra can be diluted or contaminated by dust emission and scattered light. A dusty system can hide small planets and complicate atmospheric retrievals by adding extra continuum emission. A variable system can create false positives if time variability is mistaken for composition, especially when data are sparse. The cleaner the system, the cleaner the inference, and Alpha Centauri may not be clean. This is why the chapter's careful definition of strange is not academic. If we misclassify dust as a planet, we waste time and build false expectations. If we misclassify a planet as dust, we miss a nearby world that could transform future mission priorities. If we misclassify an artifact as either, we undermine trust in the method and in the instrument. The stakes are scientific, but they are also strategic. Webb is not just observing Alpha Centauri, it is training us for what comes next. Now we tighten the chapter toward a peak, by showing how the planet versus dust comparison becomes a cliff edge in interpretation. A planet-like point source with a stable position and repeatable spectrum would be a major result, because it would imply a bound object with a measurable thermal signature. A dust-like excess with silicate features and extended structure would be a major result of a different kind, because it would imply active replenishment and dynamical sculpting. The strange part is that both outcomes imply an active, structured system where we expected quiet. Either way, the system refuses to be a simple neighbour, and the visuals, if we could hover beside Webb, would reflect that tension. We would see a bright star whose light blooms into structured rings. Then we would see subtraction peel those rings away like layers of glare. What remains would be faint, almost hesitant, and yet stubbornly present in the same place across tests. That remnant is where interpretation begins, and where disagreement can live. The mystery is not that the signal is faint. The mystery is that it persists. We end with the investigative posture that the next chapter will inherit, because the story is not finished by a single dataset. The anomaly is not a headline until it survives repetition, cross-checks, and modelling that tries hard to explain it away. Webb has given us a new language for Alpha Centauri, but the language is subtle and easy to mistranslate. The closer the system is, the more it humbles us, because small errors and small structures both become visible. In that proximity, confidence must be earned. Next, we take the candidate's strange signatures and ask which ones can survive the full battery of tests without special pleading. We follow the evidence from infrared curves to physical environments, and from physical environments to habitability stakes. The question remains sharp, and it remains grounded in method. What exactly is strange in Webb's infrared view of Alpha Centauri, and what does that strangeness mean for hidden worlds and fragile atmospheres? The strange infrared hint is no longer just a detection problem, because it refuses to stay inside the box of instrumentation. It becomes a habitability problem because dust, flares, and atmospheres share the same physics. In the infrared, heat is information, yet heat can come from many sources that look deceptively similar. A faint excess can be a planet's thermal glow, a belt of grains, or even a calibration edge where optics and astrophysics briefly blur. We return to the documentary's central question, and we let it sharpen rather than soften. What exactly is strange in JWST's infrared view of Alpha Centauri? And does it point to hidden planets, dust chemistry, or something deeper about life? The mystery is not only what glows, but why it glows in that particular way. In a system this close, even a small anomaly feels like a message. Yet the language of that message is radiative transfer. Now we make the transition to habitability explicit, because the stakes depend on it. If the system is active and dusty, then Earth-like becomes a moving target. A planet can be Earth-sized and still live inside an environment that Earth never had to endure. Habitability is not just a map coordinate. It is a long negotiation between energy, chemistry, and time. Habitability begins with a simple idea that is easy to misuse, especially when it is reduced to a single number. The habitable zone is the range where liquid water could exist on a surface. It is a thermodynamic argument first, an energy balance between starlight absorbed and heat radiated away. In plain terms, it asks whether a planet can keep water from boiling away or freezing solid. That range depends first on stellar luminosity, which sets the baseline flux at a given distance. More luminous stars push the zone outward, while dim stars compress it inward. In practice, astronomers often express this as an effective stellar flux, because it compares different stars on the same scale. Behind that shorthand sits the Stefan, Boltzmann law, tying temperature to the fourth power of radiated energy. That range also depends on the planet's atmosphere, because air is not just a blanket. Greenhouse gases, clouds, and albedo can shift surface temperatures dramatically. A thin atmosphere can fail to distribute heat, while a thick one can trap it and resist freezing. Even the planet's rotation and circulation matter, because winds and oceans decide where heat actually goes. Even the same gas can behave differently under different stars, which is a subtlety often lost in popular summaries. A redder stellar spectrum interacts with clouds and aerosols in different ways than a bluer spectrum. That means the same planet can move in or out of habitability when the star's colour changes. Rayleigh scattering weakens under red light, for example. So a sky can absorb more energy even with identical composition. So we draw the first hard line in the narration, and we keep it in view for the rest of the chapter. Habitable does not mean inhabited, and it does not mean stable. It means only that in principle, liquid water is not immediately forbidden by temperature. The zone is a permission slip, not a promise. A planet can sit in the right flux range and still be sterile, because climate is not the only gatekeeper. It can lose its air, freeze out its water, or be chemically misleading. It can also be habitable only briefly, an interlude between catastrophic phases. On geological timescales, briefly can still mean tens of millions of years, which is long for climate and short for evolution. We split the system into 3 habitability regimes because the stars are 3 different engines. Alpha Centauri A is sun-like, B is cooler and dimmer, and Proxima is a flare-driven red dwarf. Their spectra, magnetic activity, and long-term evolution diverge in ways that matter for every molecule we might measure. The same infrared band can therefore encode 3 different environmental stories. Alpha Centauri A offers the familiar temptation, and the visuals almost write themselves. A sun-like spectrum and steady output suggest a classic Earth analogue could exist. In a wide shot, the star feels comfortable, yellow-white, stable, and quietly luminous. Historically, sun-like stars were the first targets for another Earth searches, because our own planet made that bias feel reasonable. Alpha Centauri B shifts the same picture, but the shift is not cosmetic. Lower luminosity moves the temperate band inward, and the spectrum is redder and slightly less harsh. That redder light changes photochemistry, because fewer high-energy photons are available to break certain bonds. A planet there might receive gentler UV, while still facing different cloud behaviour and different seasonal contrasts. Proxima flips the logic entirely, and it does so with brutal efficiency. Its habitable zone is close, and closeness means stronger tides, stronger winds, and stronger exposure. In a tight orbit, a planet lives inside the star's magnetised weather, not merely under its light. Visually, the star is small and crimson, but the environment around it can look electrically alive: arcs, particles, and invisible radiation shaping the air. We pause on the key misconception that drives many headlines, because it distorts everything that follows. The habitable zone is not a guarantee, it is a starting coordinate. It is where the questions begin, not where the answers end. If anything, the zone tells us where to look for complicated worlds, not where to expect easy ones. In older astronomy, the habitable zone was sometimes treated like a cosmic shoreline, a place where oceans might simply appear. Modern exoplanet science has made that view harder to defend, because we now see how violently planets can diverge. Venus and Earth sit close together, yet their atmospheres tell opposite stories. That lesson has only sharpened since the first exoplanets were confirmed in the 1990s, when planets stopped meaning like ours by default. Now we pivot to Proxima, because it is where habitability is most visibly under fire. It is also where biosignature interpretation becomes most fragile. If we can learn to read Proxima's environment honestly, we can read almost any environment more carefully. The nearest red dwarf becomes a training ground for scientific humility. Proxima's flare behaviour is not a side detail, and it is not merely a spectacle for light curves. It is a climate-forcing mechanism that can dominate atmospheric evolution. A flare is a magnetic event, but its consequences are chemical and geological. The energy released is stored in twisted magnetic fields, then dumped into radiation and particles on timescales of minutes. Flares deliver bursts of UV and X-rays, and the timing matters as much as the intensity. Those photons break molecules, heat up atmospheres, and change chemistry faster than geology can respond. In the upper layers, where densities are low, a single energetic photon can start a cascade of reactions. The result is a temporary new atmosphere, one with different radicals, different temperatures, and different escape rates. In visual terms, the planet's sky becomes a laboratory, and the lab lights flicker unpredictably. During a flare, the upper atmosphere expands like a heated lung swelling into space. That expansion makes it easier for particles and radiation to do damage. The exobase rises, the collision rates drop, and the boundary between air and space becomes less of a wall and more of a gradient. Particle storms add a second blow, and they are often coupled to the same magnetic eruptions. Energetic protons and ions erode atmospheres through ion pickup and sputtering. If the planet lacks strong shielding, the star's wind can interact directly with the upper air. In extreme cases, the interaction can carve a comet-like tail of escaping ions, an auroral signature stretched into a loss channel. We define the two main escape pathways in plain terms because the mechanisms can sound abstract until they are pictured. Hydrodynamic escape is a heated upper atmosphere flowing off like a wind. When the gas becomes hot enough, it can behave less like a static layer and more like a fluid outflow. Once that flow begins, lighter atoms can drag heavier ones with them, changing the planet's composition as well as its mass. Sputtering is impact erosion, and the word is almost literal. Incoming particles knock atmospheric atoms into space, especially when the exobase is expanded. It is a microscopic sandblaster applied to the edge of a world. Over time, sputtering can preferentially remove certain species, subtly rewriting the ratios we later try to interpret as clues. Both processes intensify when the planet is close, because the energy input is higher and the wind is denser. Proxima's habitable zone is close enough that the upper atmosphere is repeatedly stressed. Over long timescales, repeated stress can become cumulative loss. The atmosphere does not need to fail in one dramatic moment. It can be worn down like stone under surf. The early history matters even more than the present, because planets inherit the consequences of their youth. Young red dwarfs stay active longer, and their habitable zones migrate inward over time. That migration is not a gentle drift for a planet's climate. It can be a sequence of thresholds. A planet can start too hot, lose volatiles, and only later enter the temperature range we label habitable. That means a planet like Proxima B may have endured a long runaway greenhouse phase, even if it is cooler now. Water can be lost early, even if conditions later cool. Once the hydrogen is gone, the planet cannot simply get its ocean back without a new source. This is why habitability is a history, not a snapshot. When water is photolysed, hydrogen escapes easily because it is light and fast. Oxygen can remain, building an abiotic oxygen atmosphere that mimics life. The atmosphere can begin to look biologically promising, even as the surface becomes increasingly hostile. A world can wear an oxygen mask while suffocating underneath it. This is the first major biosignature trap, and it is a trap built from real chemistry. Oxygen can be a false positive in flare-battered systems, because loss processes can manufacture it. The signal is not fake, but the interpretation can be. The more violent the escape, the more persuasive the illusion can become. We add the second trap, and it is a natural extension of the first. High UV can produce ozone from abiotic oxygen, creating an O3 signal that looks reassuring in isolation. Ozone is often treated as a protective layer, yet its presence alone does not guarantee a living source. In fact, ozone can form efficiently whenever oxygen and UV share the same sky. Now we add the third trap, which is a false negative that cuts in the opposite direction. Flares can destroy methane and other reduced gases, erasing a living planet's signature. A biosphere could be working, yet the atmosphere could look chemically quiet. The silence would not mean absence. It could mean the star is constantly editing the evidence. So Proxima's violence cuts both ways, and that symmetry is what makes the system so instructive. It can create oxygen that is not biological, and it can remove gases that are biological. The same star can manufacture optimism and then erase it. The question becomes whether any atmospheric pattern can remain stable enough to be read. We make the key inference that drives the chapter's tension, and we treat it like a rule of reading. Biosignatures are not single molecules, they're chemical contexts. In practice, that means we must ask what reactions are possible and what sources can sustain them. A spectrum is a snapshot of an ecosystem of reactions, not a single fingerprint. Oxygen alone is ambiguous, because it can be produced by photolysis and escape. Ozone alone is ambiguous, because it can follow oxygen without biology. Even water vapor can be ambiguous if it's only a transient upper atmosphere trace. Under strong irradiation, water can be present aloft while the surface is already dry. The strongest biosignature arguments use combinations, because combinations encode constraints. O2 with CH4 out of equilibrium is harder to sustain without a constant source. On Earth, that constant source is life, but the lesson is broader. The atmosphere becomes a ledger of ongoing processes. If the ledger shows rapid replenishment against rapid destruction, something powerful is at work. CO2 provides climate context, and it also provides a baseline for photochemistry. It sets greenhouse strength, indicates volcanic cycling, and shapes photochemistry under different UV regimes. A CO2-rich atmosphere can be stable and lifeless, yet it can also be the stage for habitability. Its absorption bands also anchor retrievals, giving modelers a reference point when other features are faint. Water vapor provides habitability context, but it is not a surface proof, and that distinction matters. A desiccated planet can still show trace H2O aloft. The upper atmosphere can carry a ghost of water long after oceans have vanished. In visuals, the planet can look blue in concept art, while the real spectrum whispers only a thin, high-altitude remnant. We emphasize the equilibrium concept without overpromising, because disequilibrium is a clue, not a verdict. Life can maintain chemical disequilibrium, but geology can mimic parts of it. The question becomes which disequilibria are robust against non-biological explanations. The most convincing cases are the ones where every plausible abiotic pathway has to work too hard. In the visuals, we can imagine the atmosphere as a layered stack of reactions, each layer responding to different wavelengths. High-energy photons drive the top, while surface chemistry and volcanism drive the bottom. Between them, transport and mixing determine what survives long enough to be observed. Even a strong biosignature at the surface can be diluted or destroyed before it reaches the altitudes we can sense. Now we introduce magnetic shielding, because it is the missing variable in many simplified habitability diagrams. A strong magnetosphere can reduce particle-driven loss. It can also redirect charged particles toward polar regions, changing where energy is deposited. On Earth, those redirected particles paint auroras, and they also reveal how a field can act like a planetary umbrella. But magnetospheres are not guaranteed, and they depend on internal structure as much as external environment. Tidally locked planets can have slow rotation, which can weaken dynamos and reduce shielding. A molten, convecting core helps, but it is not assured for every rocky world. Composition, cooling rate, and even early impacts can decide whether a dynamo lasts. Even without a strong magnetic field, survival is not impossible, and we avoid turning magnetism into a single-point failure. A thick atmosphere can absorb energy and keep the surface protected. Dense air can also increase recombination rates, allowing some damaged molecules to reform. In other words, a planet can sometimes trade shielding for sheer atmospheric depth. An ocean world can also buffer extremes, and the buffering is physical as well as chemical. Water's heat capacity and circulation can move energy and stabilize climate against day-night contrasts. If the planet is tidally locked, an ocean can transport heat from the day side to the night side more effectively than land. Sea ice, currents, and even cloud decks can become the difference between collapse and persistence. A planet with high gravity can retain gases better, because escape requires more energy. A super-Earth could hold onto an atmosphere longer, though it might become too thick. A thick atmosphere can push the surface toward high pressure and high temperature, which complicates habitability in another direction. The same retention that saves water can also bury a surface under crushing air. We keep the uncertainty honest, because the story is not served by pretending we know what we do not. We do not know Proxima B's true mass, composition, or magnetic state, and each unknown changes the outcome. Even the presence of additional planets can reshape long-term stability and impact rates. In a compact system, resonances can quietly sculpt climate by sculpting orbits. At this point, the narration can linger on a simple but unsettling image. A potentially habitable world circles so close that the star fills a large fraction of its sky. The same proximity that makes the planet easier to detect can make it harder to live on. The horizon might glow red at noon, while the upper atmosphere flares with invisible radiation. Now we shift to Alpha Centauri A and B, because the binary offers a different kind of stress. It is calmer in radiation, but complex in gravity. The environment is less like a storm and more like a slow, persistent tug. The camera can widen to show two suns orbiting their shared center, bright points tracing a measured, repeating geometry. Compared to Proxima, A and B are likely less flare-dominated, especially in the most destructive high-energy bands. Their radiation environment is closer to what Earth evolved under. That does not make them safe, but it changes the dominant hazards. A quieter UV history can preserve atmospheres long enough for slow processes, like carbonate, silicate cycling, to matter. That calmness matters for atmospheric retention, because high-energy photons are the usual accelerant for escape. Lower high-energy flux reduces hydrodynamic escape and slows photochemical destruction. Over billions of years, a modest reduction in loss rate can be the difference between a thick atmosphere and a thin remnant. In habitability terms, that difference can separate a stable ocean from a world of bare rock. Historically, binary stars were once treated as poor places to look for planets, because the dynamics seemed too complicated. That assumption has eroded as surveys have found planets in binaries and even circumbinary systems. The lesson is not that binaries are easy, but that nature is willing to build in places we once ignored. The Kepler era, in particular, forced the field to admit how diverse stable architectures can be. But the binary introduces long-term orbital forcing, and this is where calm light meets restless motion. A companion star can pump eccentricity, alter insolation cycles, and reshape climate stability. Even small changes in eccentricity can change seasonal extremes and long-term ice behavior. A planet can be temperate on average, yet swing between harsh states that challenge persistence. We restate the stability constraint in habitability terms because it is not enough to be warm today. A planet must not only be temperate, it must remain dynamically stable for billions of years. Stability is the quiet prerequisite for evolution, whether biological or merely geological. Without it, chemistry resets too often for complex feedbacks to accumulate. Circumstellar orbits must stay close to each star, because the companion's pull grows disruptive farther out. The companion's perturbations grow with distance and can destabilize marginally placed habitable zone planets. In the middle region between the stars, stability can give way to chaos on astronomically short timescales. The safe zones are real, but they are bounded, and the boundaries are sharp. Circumbinary orbits must stay far out, because the planet must orbit both stars as a single gravitational source. That can place temperate conditions at different distances, depending on combined luminosity and orbital geometry. The planet's year becomes a composite rhythm shaped by the binary's own dance. In visuals, the sky can show two suns weaving patterns that never quite repeat the same way. We underline the key difference between possible and probable, because the documentary's tension depends on that distinction. Stability zones exist, but formation and long-term climate are separate filters, A stable orbit is a stage, yet the play still needs actors and time. Planets must form, migrate, and survive the early chaos of impacts and disk evolution. The binary also changes the sky a planet sees, and this is not just poetic. A second sun can add periodic light, changing seasonal patterns and photochemistry. On some days, the second star might be a bright object that casts shadows, while on others it might be absent from the sky. Even the direction of shadows can become a subtle climate variable because it changes how surfaces and clouds absorb energy. The extra illumination can be small or significant, depending on orbital phase and the planet's own orbit. It can also complicate ice albedo feedback and cloud regimes. Climate models show that small periodic forcings can sometimes trigger large transitions when a system sits near a threshold. If a planet is already close to glaciation, a modest extra pulse of light can matter. So A and B offer a trade, and it is a trade that feels almost designed for narrative. Less flare violence, but more gravitational complexity, and potentially stronger long-period climate cycles. The hazards are slower, subtler, and therefore harder to rule out. A world there might keep its atmosphere, yet struggle to keep its climate steady. Now, we connect the binary back to the strange JWST hint, because the anomaly may be environmental rather than planetary. If warm dust is real, it implies ongoing collisions. Dust is not just debris, it is a sign that something is grinding, breaking, and replenishing material faster than it can disappear. In a close system, dust grains are short-lived, so a persistent glow implies a persistent source. In the infrared, warm dust can glow like a faint veil near the stars, and the camera can make it look almost smooth. Yet physically it is a swarm of grains, each one absorbing starlight and re-radiating heat. The grain size distribution matters, because small grains heat and cool differently than large ones. Composition matters too. Silicates, carbon-rich grains, and ices radiate with subtly different spectral fingerprints. Ongoing collisions imply impactors, and impactors are not neutral for habitability. Impactors can strip atmospheres, deliver volatiles, and reset surfaces, depending on size and frequency. A single large impact can erase climate stability for millions of years, while many small ones can steadily alter atmospheric chemistry. The same impacts that sterilize can also seed, which is why the interpretation never stays simple. A dusty inner system can therefore threaten habitability, and it can do so in more than one way. It can also supply water and organics, especially if comets are being driven inward. The same dynamical stirring that creates dust can also move icy bodies across temperature boundaries. In visuals, a quiet belt becomes a shimmering river of particles, with occasional bright flashes where collisions briefly heat fresh debris. We keep the ambiguity sharp because it is the chapter's emotional engine. The same dust glow can mean danger, or it can mean delivery. It can be the signature of a system that never settles, or the signature of a system that keeps resupplying the ingredients for oceans. The infrared does not tell us which story is true by itself. It only tells us that something is active. Now we bring JWST into the habitability question, with strict limits that protect the story from overclaiming. JWST can measure spectra, but it cannot declare life. Its power is real, yet it is bounded by geometry, brightness, and the physics of inference. The telescope is a translator, and translation always risks losing meaning. JWST's best path is atmospheric characterization when geometry cooperates, because transits offer a clean technique. Transmission spectroscopy needs transits, and transits are unlikely for A and B. The probability is low because the alignment must be nearly perfect from Earth's viewpoint. Even a rich planetary system can hide from us if its orbital planes are tilted by a few degrees. For Proxima, transits are also not guaranteed, and this uncertainty is central to the observational strategy. Proxima B has not been confirmed as transiting, which blocks the cleanest atmospheric route. Without transits, we rely on subtler signals that are easier to confuse with stellar variability. In a flare star, the star itself can mimic the very spectral changes we want to attribute to a planet. Emission spectroscopy and phase curves can help for warm planets, because they track a planet's own thermal glow. But small temperate worlds are faint, and stellar contamination can dominate. In the mid-infrared, the contrast improves, yet the absolute signal remains tiny. The planet's photons arrive mixed with instrument noise, background emission, and the star's own complex infrared behavior. Nearby brightness helps signal to noise in principle, and Alpha Centauri is the nearest bright laboratory we have. It also worsens systematics, because saturation, PSF residuals and scattered light become severe. The very photons that make detection possible can also overwhelm the detector's clean behaviour. In visuals, the star's image blooms and spills, and the planet's signal hides in the structured leftovers, so JWST's role is constrained and strategic, and the documentary treats it as a tool rather than an oracle. It can constrain dust composition, temperature distributions, and possibly detect bright companions. It can also test whether an infrared excess is spatially extended, which would support dust over a point-like planet. Spatial extension is a simple clue, yet it can decide between two radically different interpretations. It can also set upper limits on atmospheric features in favourable cases, and those limits are not trivial. Upper limits still matter, because they eliminate classes of atmospheres. If methane must be below a certain level, or if water features must be muted, the space of plausible worlds shrinks. Science often advances by narrowing, not by declaring. We clarify what molecules JWST can plausibly probe in the infrared, because the audience deserves specificity. CO2 has strong bands, and water vapour leaves broad signatures. Methane can be detectable in some regimes, while ozone is harder in the infrared than in the UV. Carbon monoxide and other photochemical products can also appear, hinting at how hard UV is pushing the atmosphere. Oxygen itself is not an easy IR target, which is a practical constraint with philosophical consequences. Many classic life discussions revolve around O2, yet the instrument's wavelength range does not make O2 straightforward. That pushes us toward proxy molecules and toward careful, multi-molecule narratives. It also pushes us toward patience, because no single dataset can carry the entire burden of interpretation. This is where false positives and negatives return, because the measurement is only the first step. JWST might see CO2 and H2O and still miss biology, because those are common outcomes. A planet can be wet in the upper atmosphere and still be dry on the surface. A spectrum can look earthy in fragments, while the whole planet is not. JWST might see a hint of methane and still be misled, because methane can be volcanic or impact-generated in some contexts. The lifetime of methane depends on UV, radicals, and atmospheric mixing. In a flare-rich environment, methane can be both produced and destroyed on timescales that confuse a single snapshot. The same observation can therefore be a clue about the star, not the planet. JWST might see a flat spectrum and still be misled, and this is one of the most frustrating outcomes. High clouds or hazes can mute features and hide the very molecules we seek. A haze layer can act like a curtain, reflecting and absorbing light before it reaches deeper atmospheric layers. In visuals, the planet becomes a pearl-like disk, bright but uninformative, with its chemistry sealed behind aerosols. So the retrieval problem becomes part of the mystery, and the narration treats retrieval as a kind of translation. A spectrum is not a direct reading. It is an inference under model assumptions. The data are real, but the mapping from data to atmosphere is many to one. Even with high signal to noise, the same spectrum can be explained by different temperature profiles and cloud decks. We state the key retrieval dependency, because it explains why experts argue even with good data. Temperature structure, clouds, and composition trade-off, and multiple solutions can fit the same data. A cooler atmosphere with fewer absorbers can resemble a warmer atmosphere with more absorbers at certain wavelengths. This is why retrievals return probability distributions, not single answers. In a flare-driven system, time variability adds another degeneracy, and it is not a minor one. A spectrum taken during quiet and during active phases can differ. Stellar spots and faculae can also imprint signals that masquerade as planetary absorption. If we do not model the star correctly, the planet's spectrum becomes a mirror of stellar complexity. That means the observing strategy matters, and it becomes part of the scientific method rather than a scheduling detail. Multi-epoch spectra can separate stable atmospheric features from transient flare-driven chemistry. Repetition can reveal whether a feature is persistent, periodic, or merely coincident with stellar activity. Over time, the dataset becomes less like a photograph and more like a time-lapse of an atmosphere under stress. Now we connect photochemistry to Proxima's UV again, because UV sets the reaction network like a hidden script. High UV can drive CO and O buildup from CO2 photolysis. If the recombination pathways are inefficient, the atmosphere can drift toward compositions that look processed, rather than alive. A planet can become chemically oxidized simply because the star keeps supplying the energy to break and rearrange molecules. If hydrogen escapes, oxygen can accumulate, and the accumulation can be dramatic. If surface sinks are limited, oxygen can persist without life. The planet can become oxygen-rich for reasons that have nothing to do with photosynthesis. In the wrong context, that oxygen becomes a siren song, calling us toward a conclusion the planet did not earn. Surface sinks are a crucial unknown, and they are a reminder that atmospheres are not isolated shells. Oxidation of crust, volcanic outgassing, and ocean chemistry can remove oxygen over time. On Earth, iron-rich rocks and reduced gases act as sinks, and their balance with sources shapes the long-term atmosphere. If a planet's mantle is more reduced, or its tectonics are weaker, the sink strength can change by orders of magnitude. So a biosignature claim must include geology, and that requirement is not optional. Without sinks and sources, we cannot interpret atmospheric abundances reliably. A planet with little volcanism may fail to replenish reducing gases, while a planet with intense volcanism may flood the atmosphere with them. Either extreme can hide a biosphere or imitate one. At this stage, the chapter can ask a question that hangs in the air without answering itself. Are we looking for life, or are we looking for a planet that can keep its story legible? In a violent environment, even a living world might have a scrambled signature. If the atmosphere is constantly rewritten, what does evidence even mean? We compress the philosophical turn that makes this the climax chapter, and we keep it grounded in physics. We are not only searching for molecules, we are searching for meaning. Meaning requires context, and context requires models that can survive contact with extreme environments. The more extreme the environment, the more conservative our claims must become. Models require assumptions, and assumptions are fragile when the star refuses to behave like the Sun. In Proxima's case, the UV and particle environment can be episodic rather than steady. In the binary's case, the orbital forcing can be slow, periodic, and difficult to sample. The universe is not obligated to give us steady-state targets, even if our instruments prefer them. Now we briefly address technosignatures, because the audience will ask, and because curiosity is part of the genre. Artificial signals are alluring, but they are not the focus here. The documentary acknowledges them as a parallel thread, not as a shortcut. In a story about interpretation, the most dangerous mistake is mistaking desire for diagnosis. Technosignature searches target radio, lasers, or waste heat patterns, and each has its own assumptions. JWST can constrain some waste heat scenarios, but that is speculative. Waste heat would have to be large, structured, and persistent enough to stand out from dust and natural thermal emission. In a dusty system, even that distinction becomes harder, because dust also glows like a low-temperature radiator. So the documentary stays grounded, and it does so deliberately. We follow astrophysics first, because the environment must be understood before any extraordinary claim. If the environment can explain the signal, we must exhaust that explanation before we reach for a stranger one. Restraint is not a lack of wonder. It is the method that makes wonder reliable. Now we tighten the chapter around the central tension, because the story is approaching its hinge. If JWST finds the right molecules, can we trust what they mean here? The nearest stars offer the best chance for detail, yet they also offer the most ways to be fooled. Proximity increases resolution, but it also increases the complexity we can finally see. In Proxima's case, oxygen and ozone can be manufactured by loss, and the manufacturing can be efficient. Methane can be destroyed by flares, erasing a living signal. Even if life exists, the atmosphere may not cooperate with our expectations. The planet could be inhabited yet spectrally ambiguous, which is a hard outcome for a field built on remote sensing. In A and B's case, gamma radiation helps interpretation, and it reduces the most aggressive photochemical distortions. But the binary's dynamics and possible dust activity complicate long-term stability. A planet might be chemically readable, yet climatically unstable on long timescales. The easier spectrum might belong to the harder climate, so the system offers no easy win, and that is what makes it worthy of a full chapter. The nearest neighbour is close enough to tempt certainty, yet complex enough to humble it. Alpha Centauri is not a single target, but a set of overlapping experiments. Each star is a different laboratory, and each laboratory tests a different weakness in our reasoning. We return to the strange infrared hint as the catalyst, because it is the thread that ties detection to habitability. If it is dust, it may signal an impact-rich environment that stresses atmospheres. If it is dust with unusual composition, it may even encode the system's collisional history. A spectrum of grains can become a fossil record of grinding and migration. If it is a planet, it may be a world we can characterize next, and a test case for biosignature logic under pressure. A nearby planet would not just be a discovery, it would be a calibration point for the entire field. It would let us compare models against a target we can revisit again and again. The closer the target, the more merciless the comparison between prediction and reality becomes. Now we set up the final chapter's resolution, and we do it in the language of method rather than miracle. The ending is not a single answer, it is a decision tree guided by new observations. Each branch is a test, and each test reduces ambiguity. The story advances by elimination, by confirmation, and by learning which uncertainties actually matter. Future missions can break degeneracies, and the documentary frames them as complementary rather than competitive. Extreme precision radial velocity can refine masses, and astrometry can reveal inclinations. With inclination, mass stops being a minimum and becomes a physical property. Once mass is known, atmosphere retention and interior models become less speculative. Direct imaging missions can separate planets from dust, and separation is the first step toward clarity. They can also measure reflected light spectra where oxygen and ozone are clearer. Reflected light carries different information than thermal emission, and it can reveal clouds, surface scattering, and atmospheric absorption. In visuals, a chronographic mask turns a blinding star into a controlled darkness, and faint worlds step out of the glare. Long baseline interferometry can probe warm dust and temperate planets in the mid-infrared, and it can do so with spatial discrimination. It can turn the dust obstacle into a mapped foreground. Once mapped, dust becomes something we can subtract rather than something we must fear. The technique is demanding, but the payoff is simple. The scene becomes separable, but the immediate next step is simpler and more demanding, because it requires patience rather than new hardware. Repeat JWST observations must test persistence, spectrum, and motion of the strange signal. Repetition can show whether the signal is fixed on the sky, evolving in time, or tied to the telescope's own behavior. In a mystery built from photons, persistence is the first form of truth. If the feature repeats and tracks the sky, it becomes an astrophysical object, and the story changes. If it rotates with the telescope, it becomes a cautionary artifact. The difference is not philosophical, it is geometric, and geometry can be tested. The camera can even visualize this as a rotating frame, where real objects stay put and artifacts slide with the instrument. If it varies like a collision cloud, it becomes a dynamical event with a timescale, and timescales are diagnostic. If it behaves like a belt, it becomes a long-lived environmental constraint. A belt implies steady replenishment, which implies ongoing stirring and a reservoir of material. In either case, the infrared glow stops being a rumour and becomes a measurable process. We close the chapter with the core message of the climax, and we let it land with quiet weight. Habitability is not a location, it is a survival story written in light. The light carries the record of violence, stability, chemistry, and time. When we read that light, we are reading not only planets, but the conditions that shape what planets can become. And in Alpha Centauri, light is complicated, because it arrives from multiple stars and multiple processes. JWST's infrared clues do not just hint at worlds, they test our ability to read them. The instrument gives us spectra and images, yet interpretation remains a discipline of restraint. The closer we get to answers, the more carefully we have to define what an answer is. The strange signal remains the thread, and it stays uncut at the chapter's end. It pulls us toward the final chapter, where the system's ambiguity becomes the point, not the failure. In the nearest stellar neighbourhood, the universe is not hiding answers, it is demanding better questions. Four light-years away, the nearest neighbour still refuses to resolve into one clean answer. JWST's infrared hints look strange because they sit at the boundary between astrophysics and measurement. We return to the central question and tighten it into a testable form. What exactly is strange in Webb's infrared view, and which physical source best predicts new data? 3 hypotheses remain on the table, and each carries a different set of predictions. The signal could be unseen exoplanets, warm dust and debris structures, or observational effects tied to stars and instruments. start with the planet hypothesis, because it is the simplest story and the hardest proof. A planet should behave like a compact source with consistent colours and motion that tracks a bound orbit. If the source is a planet around Alpha Centauri A or B, its position should shift measurably over months. The shift should follow Keplerian arcs, not subtraction patterns or roll-angle geometry. A planet's spectrum should also be comparatively smooth across adjacent infrared bands. Any broad molecular shaping should be stable across epochs, aside from predictable phase-driven brightness changes. The planet hypothesis predicts corroboration in other methods, even if the planet is not directly imaged. Radial velocity should show a coherent periodic wobble, and astrometry should show a matching sky plane reflex. Now the dust hypothesis, because warm dust is the most natural infrared emitter and the most deceptive. Dust can create excess, asymmetry, and apparent point sources when clumps sit near the resolution limit. If the signal is dust, it should look extended with deeper imaging, and its surface brightness profile should match disk physics. Its spectrum should tilt like grains, not like a single temperature body. Dust also predicts structure tied to the binary's dynamics, not random placement. Rings, gaps, and clumps should align with stable zones, resonances, and the time-dependent forcing of A and B. Warm dust in an old system demands replenishment, which is itself a clue. A sustained excess implies ongoing collisions, comet delivery, or resonant trapping driven by unseen bodies. Dust predicts evolution that is slower than detector artifacts but faster than stellar aging. A collision cloud should shear and fade, while a belt should persist with repeatable geometry. Now the variability and artifact hypothesis, because Alpha Centauri is a worst-case bright target. Saturation, persistence, scattered light, and PSF mismatch can manufacture a symmetry that looks astrophysical. If the signal is instrumental, it should rotate with the telescope and change with reduction choices. It should correlate with detector history, centering errors, and wavelength-dependent PSF structure. If the signal is stellar variability, it should track activity indicators and timescales. Spots, faculae, and flares should imprint correlated changes across bands and across repeated visits. Proxima adds a special warning because its flares can mimic transient infrared behavior. Any Proxima-associated excess must be checked against contemporaneous activity monitoring and proper motion tests. Now we synthesize what the three hypotheses share, because the overlap defines the next steps. All viable explanations must survive multi-epoch repetition, multi-band consistency, and independent confirmation. The immediate observational priority is time, because time turns pictures into physics. Multi-epoch JWST follow-ups can test persistence, motion, and variability with the same instrument and comparable systematics. Those JWST revisits must be designed to break degeneracies, not merely to add exposure. Multiple roll angles should separate sky-fixed emission from instrument-fixed residuals with geometric clarity. Filter choices should bracket temperatures and grain features so color becomes diagnostic. If silicate-like structure appears consistently, dust becomes more likely than a planet-like continuum. Repeat observations should also sample the binary's changing configuration, because geometry matters here. If a feature tracks the companion's glare pattern, it points toward subtraction complexity. JWST alone cannot close every loophole, so the plan expands outward to complementary methods. Ground-based extreme adaptive optics can probe near-infrared companions at small separations with different systematics. High-contrast imaging from the ground can also map scattered light dust if it is bright enough. Even non-detections constrain albedo, grain properties, and the spatial extent of any disk. Radial velocity campaigns remain essential, even when activity complicates the meter-per-second regime. Long baselines can rule out giants, refine limits for super-Earths, and test periodicities suggested by imaging. The binary demands careful disentangling of blended spectra, and that is now a mature craft. Activity indicators, line-by-line analysis, and simultaneous reference calibration can reduce false planet claims. Astrometry is the other pillar, because it breaks the inclination problem that haunts radial velocity. Microarc second-class measurements can turn minimum masses into true masses and confirm orbital planes. Gaia already tightens the local reference frame, and future astrometric efforts can target the remaining parameter space. A confirmed astrometric wobble would force the planet hypothesis into focus. If the signal is dust, Astrometry still helps by constraining unseen perturbers. Dust structure often implies planets, and planets imply measurable gravitational signatures when the data are precise enough. Now we widen to the mission context because Alpha Centauri is a proving ground for the next era. Upcoming observatories will not just revisit the system, they will change what is observable. Roman's coronagraph will mature high-contrast techniques and wavefront control, even if Alpha Centauri remains challenging. The engineering lessons translate directly into future direct imaging flagships. Concepts like Habitable Worlds Observatory aim at reflected light spectra of Earth-like planets around nearby Sun-like stars. Alpha Centauri A and B sit near the top of that target list. Direct imaging needs two things that dust can sabotage: contrast and a clean foreground. Measuring exozodiacal dust is therefore not a side quest. It is mission-critical reconnaissance. Mid-infrared interferometry concepts push even harder on the dust problem by spatially separating warm belts from temperate planets. If built, they could map exozodi and search for thermal worlds together. As these capabilities grow, the strange JWST hint becomes a planning constraint and a scientific opportunity. It tells us whether the nearest system is clear enough for Earth twin imaging. Now we address the space exploration angle, because proximity turns astronomy into destination thinking. Alpha Centauri remains the nearest plausible interstellar target because physics rewards closeness with shorter travel times. We keep propulsion discussion grounded because the documentary is about evidence, not fantasy. Concepts like laser-driven sails and fusion studies motivate interest, but they do not substitute for data. The real point is strategic, not cinematic, and it is already happening. Each new map of dust and planets reduces mission risk and turns a star system into navigable knowledge. Now we pull back to the cosmological takeaway, because nearby systems anchor big claims. The frequency of planets, the evolution of dust, and the stability of atmospheres all depend on local benchmarks. Alpha Centauri tests formation models in a binary, where disks are truncated and stirred. If terrestrial planets exist there, our theories must explain how they assembled and survived. Alpha Centauri also tests dust evolution in mature systems, where warm excess should be rare. If warm dust is real, it forces new accounting of replenishment and long-term dynamical stirring. Proxima tests atmospheric survival under flare-driven chemistry, which matters because red dwarfs dominate the galaxy. If biosignatures are hard to read there, our detection statistics must adjust. Together, A, B and Proxima form a compact laboratory for habitability logic. They show how biosignatures depend on stellar context, dust foregrounds, and the limits of remote sensing. Now we resolve the mystery in the only honest way a final chapter can. The strange finding is not a single answer, it is a narrowing corridor of explanations. If follow-up shows orbital motion and consistent colours, hidden planets move from speculation to census. If it shows extended emission and grain-like spectra, dust becomes the system's dominant story. If it collapses under roll-angle tests and calibration scrutiny, the lesson is still valuable. It teaches how close, bright systems stress our instruments and how to harden future searches. Either way, Alpha Centauri stops being a mythic neighbour and becomes a measurable, testable world of data. The system's closeness does not grant certainty, but it grants repeated interrogation. We end with a forward-looking promise that fits the evidence and the tone. 3 stars bound together, A, B and Proxima, now function as a living laboratory for NASA's next era. Every new dataset narrows the unknown, and the narrowing is the real discovery. The nearest neighbour is becoming a mapped place, and the strange infrared hint becomes a guidepost. The question that opened the film remains, but it is no longer unanswerable. Webb did not give us one revelation, it gave us a path to resolve what is real. Alpha Centauri looked like the perfect nearby laboratory, yet Webb showed us how proximity can make certainty harder, not easier. In infrared, starlight, dust heat, binary dynamics, and Proxima's violence stack together, and the system becomes a single, shifting riddle. Across A and B's time-varying gravity, Proxima's flare-driven chemistry, and Webb's own structured optics, we learned that strange is rarely one thing. It is usually an overlap. The binary rewrites what normal means, carving stability zones and resonances that can sculpt dust into rings, gaps, and clumps. Old stars should be dust poor, so any warm excess is suspicious, unless collisions or comet delivery keep replenishing it. Proxima, meanwhile, offers the opposite trap, a habitable zone that is easy to find, and an environment that may be hard to survive. And through it all, Webb's advantage and limitation stayed linked, because infrared turns heat into information, while demanding we master saturation, persistence, subtraction, and the deceptive beauty of a PSF. That is why the Alpha Centauri anomaly matters, even before it is solved. If the glow is a planet, it changes the nearest neighbour story from almost solved to already inhabited by worlds. If it is dust, it becomes both a tracer of hidden architecture and a fog that could sabotage future biosignature searches. If it is an artifact, it still teaches the same lesson, that the path to discovery runs through disciplined doubt, repeated tests and models that survive every attempt to break them. So what exactly is strange in Webb's infrared view, and does it point to planets, dust, or something more profound about habitability? Right now, the strangest thing is not the glow itself, but how many believable stories can produce it, until time, geometry, and spectrum force only one to remain. The deciding evidence is wonderfully specific and stubbornly patient. A hidden planet should keep stable colours across filters, stay point-like, and shift position with Keplerian motion, while independent radial velocity or astrometric wobbles begin to agree. Warm dust should look extended or structured, show grain-shaped spectral features, align with resonant zones, and evolve like a belt or collision cloud rather than a moving dot. An artifact or stellar variability should collapse under roll-angle tests, calibration changes, persistence checks, or flare-correlated variability, rotating with the instrument instead of the sky. That is why the next Webb campaign cannot simply go deeper, it must go smarter. Multi-epoch visits spaced to catch expected orbital motion, paired roll angles that swap what is optical for what is astrophysical, and a filter set chosen to separate black body-like emission from grain chemistry will break the degeneracy. Those observations will tell us whether the signal repeats with the system, drifts with time, or vanishes when the instrument's fingerprints are properly accounted for. And beyond the mystery, another question has been hiding in plain sight. Is Alpha Centauri clean enough to become a true destination for future Earth twin imaging? If Webb is seeing a bright exozodiacal foreground, Roman and the Habitable Worlds Observatory may face a harder contrast problem, and biosignature retrieval could become a battle against dust confusion. But if the system is relatively clear, or if the dust is mapped and predictable, then Alpha Centauri becomes the nearest stage where direct imaging can finally move from possible to practical. 4 light-years away, the closest stars tempt us to believe we're only one good image away from certainty, but Webb has shown that nature rarely offers answers without context. The real discovery may be this, that habitability and biosignatures are not read off a single world, they are inferred from an entire system's moving light, dust, dynamics, chemistry, and time. In the end, Alpha Centauri does not feel less familiar because it is strange, it feels more honest. It reminds us that the nearest neighbour can still surprise us, and that the difference between a mirage and a new world is the discipline to return, measure again, and let the sky keep its own score. Watch for the next multi-epoch Webb results, and when they arrive, ask not only what we found, but what finally made the answer unambiguous.